at Stanford University for hosting us in this way. I'm Frank Sesno. As I like to say, I'm your tour guide and moderator for the day. Normally, I live in a place called Washington, D.C. It's really nice to be here with you today. I've been working with Kavli for some time now. I am a journalist, was at CNN for many years, and I now am the director of the School of Media and Public Affairs at the George Washington University. And what Kavli does, and what I'm happy, thrilled, honored to help do, is to communicate science, to connect science, to support science, and to reward science. They're doing everything that's right in the world, rewarding inquiry, discovery, science, and humanity. The Kavli Prize, as you may know, and if you don't, you should, there will be a short quiz before you leave this afternoon, is a partnership between the Norwegian Academy of Science and Letters, the Kavli Foundation, United States, and the Norwegian Ministry of Education and Research, and you'll be hearing some more about that. The Kavli Prizes recognize scientists for pioneering advances in our understanding of the existence at its biggest, smallest, and most complex scales, celebrating this year the 10th anniversary of the Kavli Prizes. I wrote a book recently on the power of questions, sort of what I do as a journalist, and there's a chapter on science. Science, I say, is the slow question, the question that builds on itself and on the shoulders of its predecessors. Questions that embrace uncertainty, which is something the rest of the world could learn in a variety of ways. So I'm fascinated by this and really looking forward to the conversations. There will be 3 panels here. Let me just walk you through briefly, and then I'm going to turn it over to the Vice Provost, Dean of Research here at Stanford. There will be 3 panels today. We'll go from small to very complicated to very big, nanoscience to neuroscience to astrophysics. We'll look and talk about what these amazing scientists have done and learned and discovered, but really more importantly, or not more importantly, as importantly, is the implications of these discoveries for the future. For those of you who are students, how many students in the room? Okay. Including my nephew there, who's a PhD candidate in physics, so go John. This conversation should highlight the future a little bit. You will all, whether you're a student or not, have an opportunity to ask questions of our panel. On your tables, you will see a piece of paper that looks like this. This is very analog, but it'll work. This will, if you don't already have it, you can download the Pigeonhole app. And I don't know if you've ever had a chance to use Pigeonhole, but it is really great. You will enter the passcode, which is listed here, and then throughout the afternoon, you can put your questions in for the panels by panel. So the questions are identified by panels. If you don't have a question, or even if you do, you can vote on other questions there, and then when I come up here with my iPad, I will see both the questions and the votes, and I will incorporate those questions into our conversations as much as possible. I said at the outset I was a journalist and CNN for many years. Fundamentally, it's being a storyteller. I love the power of stories and stories to help us record and remember, motivate and act. And every story has a powerful character. As I say to my students, compelling characters overcoming obstacles to achieve a worthy outcome. We have great characters here today, characters who will inspire us and from whom we will learn. But before we get to that, let's set up the event in style and with some context, and I'd like to welcome Ann Arvin, who's the Vice Provost, Dean of Research here at the one and only Stanford University. Ann, it's all yours.
Thank you very much, Frank, and good afternoon. It is my great privilege to welcome all of you to Stanford University, and I can say on behalf of my Stanford colleagues that we are all honored that we were asked to host this first celebration of the Kavli Prizes that is taking place outside of Norway. So a very special occasion, and we're very glad that you're here to celebrate with us. I'd like to offer a special welcome to the representatives of the Norwegian Academy of Sciences and Letters and the Norwegian Consulate General in San Francisco, who are here with us today, and of course to our friends from the Kavli Foundation. Welcome. In coming together to establish these Kavli Prizes in Astrophysics, Nanoscience, and Neuroscience, you have certainly established not only one of the world's most prestigious scientific awards, but you've also created partnerships that really illuminate the vital importance of basic science to humanity. This award and the science that it recognizes, both recognizes and inspires, promises to help advance fundamental discovery for many generations. So we thank you for endorsing this noble goal and for bringing us together for what promises to be a very exciting symposium. Now, let's give a very special and warm welcome to our Kavli Prize laureates. We are here first and foremost to celebrate your remarkable accomplishments as internationally renowned scientists. I also want to welcome your invited guests. We know that none of us can do our best work without the support of family and friends. Every scientific breakthrough reflects their support, along with the hard work and dedication of the members of the research teams. So thank you for your role in enabling these exceptional achievements by our laureates. We're very glad that you are all here today. So laureates and guests, thank you for being here. I'm also happy to say that Stanford has been home to 4 of today's Kavli Prize honorees at some point during their careers. So we're pleased that many of their Stanford faculty and friends and their students are here in attendance. Very warm welcome also to the colleagues and students of the other Bay Area Kavli honorees who are from our neighboring universities, UC San Francisco and UC Santa Cruz, and from IBM. Welcome to all of you. And finally, I'll just end by saying that Stanford is especially proud to be the home not only of several of today's honorees, but also to our Kavli Institute for Particle Astrophysics and Cosmology. You may know this is the second of the 20 Kavli institutes that Fred Kavli and the Kavli Foundation have established around the world. Having this Kavli Institute at Stanford has given me the special privilege of working with our next speaker, Bob Conn, who is the president and CEO of the Kavli Foundation. Welcome, Bob.
Well, thank you, Anne, and thank you all for coming. I must say, when I spoke first into this microphone as a test, it wasn't me. The baritone is much deeper than my natural voice. It is terrific to actually be here in the Bay Area to honor one of the places with some of the greatest academic institutions in the world. And that's reflected in the people who've won Kavli Prizes here. The fact that there are 8 of you here. I'll say a little bit more about this, but let me simply say, everybody can do arithmetic, and there have been 40 Kavli laureates. 8 are from this area. So 20% of the winners over 5 cycles come from here. It's really quite amazing. As Frank Sesno remarked, this is really a true partnership. It's been a lovely partnership to be working together. The Kavli Foundation with the Norwegian Academy of Science and Letters, the Norwegian government. And when we say the Norwegian government and its ministries, we also mean, everything in Norway. When we go there and celebrate, and the Kavli Prize winners can reflect on their time when they were in Oslo, either the king or the crown prince attends and gives the prizes. The ceremonies are extraordinarily special. The dinner is held in the same place where the Nobel Peace Prize is given, by the way, by Norway. And so it's a week of celebration of science that really is less formal than the other major prize you know about, and a hell of a lot of fun. And I think our Kavli laureates appreciate that. So I wanted to remark just briefly, because Ole Sejersted, who is the president of the Norwegian Academy, will tell you more about the prize in the next talk. But the numbers impressed me when I looked at them. So there have been, over 5 cycles, 40 winners. And by the way, there have never been more than 3. There have been any number of years where there have been 2 in a subject area. Only once has there been a single prize winner win the whole prize, and that was the great Millie Dresselhaus from MIT. She was called the mother of carbon. She was a remarkable nanoscientist, and she's been our sole, so far, winner of the Kavli Prize. She passed away about a year ago, but boy, was she amazing, and a pioneer as a woman in science. Remember, when she started out, it was the late 40s and early 50s. It wasn't so easy, and it still isn't easy enough, or as easy as it should be. Anyway, so 40 winners, you did the arithmetic, and so many have come from here in Northern California. I just think it's a tribute to what's happened over the last 120 to 140 years in the United States. How did it come about that we end up with 16 or 18 of the top 20, 25 universities in the world? How does it end up that we have so many distributed around the country? How did it end up that there's so many here in the Bay Area? It's kind of a remarkable story of not just academic development in the United States, but also the development of science, innovation, entrepreneurship, and all the rest of it. And so I say that because that fits to a degree Fred Kavli. Fred Kavli came from Norway, and his story is the quintessential American immigrant story. He came, he did have a degree, he didn't come as a poor immigrant. On the other hand, he didn't have very much in his pocket. And he arrives in 1955 or 6, and can't get to the country, by the way. Had to go to Canada first, spend a year working with the Imperial Chemical Industry, ICI. With that job, he could get into the US. Came here where his father had come in 1912 or 14, and he always thought, if I ever have a chance, I'm going to go to San Francisco. Found out that it's foggy in San Francisco and cold. Went down to Southern California and settled there and basically made the rest of his life there. So he would always say, at least he said to me and many others, Norway gave me my roots, America gave me everything else. And somehow he got inspired while in Norway about the magic of nature. And when time came to think about what to do with the fortune he'd accumulated, he decided to give it all back to basic science. When he passed in 2013, essentially his entire holdings are now the Kavli Foundation. We're approaching $700 million in resources. And just to give you a sense of what that means, it allows us to spend $35 million a year, roughly speaking. But we spend it all on science or on helping the public better appreciate and understand science and rewarding scientists. So I'll give you a comparison. Many of you know the Sloan Foundation, a remarkable foundation, and founded in 1932. They have a $2 billion endowment. They spend about $75 or $80 million a year. They're very well known in science. They spend $25 million in science. So do we. So from a spending on science, basic science, the foundation has an extraordinary corpus, and Fred left us with a great opportunity to help scientists do great work. As was implied, the foundation doesn't just partner in giving the Kavli Prizes, though that's one of the extraordinary things that happens. But we also have, as Anne mentioned, 20 Kavli institutes around the globe. They're actually in 4 fields, neuroscience, nanoscience, astrophysics, cosmology, et cetera. It's one field. And we have a couple in theoretical physics. And so that adds to 20, 14 in the United States, 3 in Europe, 3 in Asia. And that means it's really international, which means we are a global foundation, supporting science globally. Now, we always will have more than 50% going to the United States, because that was what Fred thought, but we are global, and that's a unique feature of us. And as Frank implied, we are more than just supporting the science. 80% of what we spend supports the basic science, goes to our institutes and other programs. But 20% or so goes to helping the public better understand and appreciate science. It goes to helping scientists become better communicators about science. We partner with Alan Alda and his Alda Center for Communicating Science. We partner with the American Association for Advancement of Science in giving the unique Science Journalism Awards that the AAAS pioneered in 1947, and we have now endowed. So is the AAAS Kavli Prizes in Science Journalism. And we just doubled the endowment, so they give 16 awards in 8 categories, and took them from just being Americans who are eligible to making it universal, making it global. That has a big impact. Journalists work and people in the media work really hard trying to help communicate science to the public. They deserve recognition too. And so the AAAS Kavli Prize, Kavli Journalism Awards are to do just that. Let me close by just remarking that the mission is really of the foundation, and how Fred got to this is a small miracle. Basic science. And what basic science means is science without thinking about an application. There's a tremendous amount of science done motivated by the need to solve a problem. Call that Pasteur. Solve a disease, I got to make things better. I'm motivated and I need basic scientific discoveries to solve a problem. But most of what we understand about the world around us did not come from trying to solve a problem. It came from curiosity. And it's not a feat or elite to be curious. It's human to be curious. And so fundamentally, supporting basic science is supporting the creation of the knowledge that forms the foundation upon which people can think about applications. But if you don't understand the fundamentals, you'll end up spinning your wheels a lot more than you should. So I want to end my little remarks by a quote that I think characterizes everything that Fred wanted and that we do at the Kavli Foundation. But it's not a quote from Fred. In 1935, the person who had the idea of and arranged for the funding to form the Institute for Advanced Study in Princeton, which is the home of Albert Einstein when he had to leave Europe, and where did he make his home in the United States? He ended up at the Institute for Advanced Study. And great mathematicians who had to leave Europe, Johnny von Neumann, Gödel, all the rest, they ended up at the Institute for Advanced Study. In 1935, he wrote a little pamphlet. And he entitled the pamphlet, "The Usefulness of Useless Knowledge." Think about it. The usefulness of useless knowledge. It's the essence of why we do basic science, because I can tell you without any fear of contradiction, those fundamental insights we will get from that quote-unquote useless knowledge is the future that we'll build together. So that's what the Foundation's about. It has a long tradition. I wish more would follow it, but in any case, we're happy to have all of you here today to honor people who are motivated by creating useless knowledge. You're right. Thank you very much.
So good afternoon, everyone. My name is Ole Sejersted, and I'm president of the Norwegian Academy of Science and Letters. And it's really a great pleasure for me to say a few words on this occasion. As you have now heard, the Kavli Prize is a joint enterprise between 3 partners. I have some slides to show, but it doesn't seem to be working. There we go. So it's a joint enterprise between 3 partners, the Kavli Foundation, and the ministry, which has now got a new name, the Ministry of Research and Higher Education, and the Norwegian Academy of Science and Letters. And this arrangement was set up by the visionary Fred Kavli, to whom we owe the foundation and the prizes. The Norwegian Academy was trusted the task of selecting the laureates and hosting the award ceremony. And in addition, the Academy is heavily involved in arranging lectures and seminars all over the world. Today, we are assembled here at Stanford to meet and celebrate the outstanding laureates from the Bay Area. The selection committees are, of course, a cornerstone of the whole prize setup. So far, they've done an outstanding job, as Bob Conn just pointed out. I want to say a few words about the international aspect. The prize was established with a clear point of view that science knows no borders, and to foster international cooperation among scientists. This is especially important these days. Politicians, many places in the world, want to build borders and prevent true and free exchange of knowledge and restrict freedom for scientists to travel, meet, and work together. In this regard, the Kavli Prizes have a very important mission. Here you see the academies that are involved in proposing committee members. We consult with the Chinese, the French, the German, American, and British academies, and set up committees according to their suggestions. And call for nominations goes out to 2,500 individuals and institutions around the world. We have just also established an oversight committee headed by the president of the National Academy of Sciences, Marcia McNutt, to evaluate the work that has been done so far. The award ceremony in Oslo is also a true international event with guests from all over the world. And the main street in Oslo, which you see here, is decorated with the blue Kavli banners. And the prize ceremony takes place in the big concert hall in Oslo. And the following official dinner, hosted by the government, takes place in Oslo City Hall. Surely, the prize week in Oslo has become the place to be in early September every other year. By the way, I'm pleased to announce that Alan Alda will be Master of Ceremony also in 2018. Some of you may not know that the Kavli Prizes were created to recognize the world's best scientists for truly outstanding work in astrophysics, nanoscience, and neuroscience, although you have learned this from the previous speakers. A partnership was born that brought together a shared passion and a commitment for groundbreaking science that benefits humanity. On that note, I would like to make another point. The international engagement and the events that are arranged worldwide also serve to promote a public understanding of scientists and their work. Unfortunately, we experience a growing skepticism to scientific knowledge and a growing resistance to the search for truth, which of course is at the core of what science is about. The Kavli Prizes also serves to turn these trends. To reach these goals, we have set up a series of activities in 2017 and 18, as you can see here. I have to go to Austin in 2 weeks' time for the AAAS meeting. And the next class of Kavli Prize laureates will be announced this May 31st. So then we come to today's event and the laureates whom we honored today and who are all from the Bay Area are Donald Eigler, Andrei, Linde, Carla, Shatz, Richard Scheller, Thomas Sudhoff, Calvin Quate, and Michael Merzenich, and Jerry Nelson. So I'm really looking forward to a very special event this afternoon. Thank you very much.
Well, thank you. Well, why don't I invite our first panel up, Don Eigler and Daniel Rugar. And I'm going to take a seat over here. And if you haven't gotten your Pigeonhole app down, feel free to do that so that you can join the conversation as we go. I have actually my iPad that I have to pick up over here. In its bright red cover. Thank you, Nadine, so that we can do questions. So, it is a great pleasure to be joined by our first two guests here. Don Eigler is a physicist, Kavli Prize laureate, former IBM fellow, won the 2010 Kavli Prize, right? Along with Andrei and Seaman for your development of unprecedented methods to control matter on the nanoscale. And we're all going to get that so we can go home and do it ourselves before we're done here today. So get ready. He received both his bachelor's and doctorate degrees from the University of California, San Diego, founding leader of the low-temperature scanning tunneling microscopy project at IBM's Almaden Research Center, and most renowned, and I think this is an awesome thing, for his 1989 demonstration of the ability to manipulate individual atoms. And when you manipulated individual atoms, you spelled something, which was?
IBM.
IBM. Purely coincidentally, but he has very good job security.
I'm so glad I got the spelling right, too.
So we're going to hear more of that. But in 2011, you left IBM and founded the Wet-Nose Institute for Advanced Pelagic Studies, which is a private institute devoted to facilitating and creating opportunities for science to conduct studies free of administrative responsibilities and financial demands. That sounds like about the best place to work in the world.
It's a boatload of fun.
Okay, so we'll talk about that. Dan Rugar here is manager of nanoscale studies and distinguished research staff member in the IBM research division. That's purely coincidental, right? Things happen at IBM.
Yeah, I've known Don for many years.
He received his PhD in applied physics from this university under Professor Calvin Quate. And you are here to talk about Calvin Quate today, Professor, among other things.
It's a fantastic honor to be here and to do the best I can to represent what Cal has accomplished.
We're going to get to a lot of really good things about this, but first a word about Professor Quate. One is Kavli Prize for the atomic force microscope, which, well, you tell us what the atomic force microscope is.
The atomic force microscope has basically revolutionized nanoscience. I mean, every laboratory that does any sort of material science or even biology has atomic force microscopes now. It's a universal tool for basically measuring the shape and size of things, and can go down to look at individual atoms and chemical bonds, and is used all over the world. And I can explain some practical applications, but maybe we'll get to that later.
We will get to that. Between 1950 and 1960, just another word on Dr. Quate here, he worked at labs, at Bell Labs in New Jersey, in Sandia, in Albuquerque, and moved to Stanford in 1961, where he was an esteemed professor of physics and electrical engineering. Where is the remote for the slides? Because we've got that. Is that up there? Great. Is that it? Yeah.
That's it?
Thank you. Because we'll have some slides here as we go along on our way. Let me start with you, Don, if I may.
Sure.
May I call you Don?
Of course.
That's okay. I can call you Professor if you'd rather. Okay.
No.
What is nanoscience?
Nanoscience is if you like, in the broadest sense, it's all components of science from the traditional areas of physics, chemistry, biology, material science, where the study is done about structures on the nanometer length scale, the structures that might only be 10, 20, 40 atoms across. That would be the scale of things.
And you got involved in this how?
I was always fascinated with small structures, and I just, as a graduate student, I was getting ready to get my PhD, and there came this word from Switzerland, from the IBM labs in Switzerland, about a new machine that was invented by Gerd Binnig and Heini Rohr, which at first did not have atomic resolution, but was getting close to achieving atomic resolution on surfaces, an entirely new way to see what was going on at a small scale. That got me really excited. And I thought about what could be done with this kind of machine if, instead of doing it the way they were doing it, it was be done at low temperatures. So I made myself a list of interesting experiments, and the list just kept on getting longer and longer and longer, and I was hooked.
You, I mentioned your incredible ability to sort of move these atoms and spell out IBM, right? Which was one of your things. What does that mean to move an atom?
I think it's like so many things. It's what it means depends upon your background and what that, the context from which you look at something like that. If you're a control freak, it's the end of the road.
Are you a control freak?
I'm totally a control freak. Ask anybody out there who knows me. They'll verify that. One of the ways I like to think about it is that if you look at the kinds of structures that mankind has been building, one of the things that we've done, starting from probably thousands of years ago, is we've ended up building smaller and smaller and smaller structures. And then being able to build things at the atomic scale by taking atoms and putting them where you want really does represent what we think is the end of the road in terms of what we'll be able to build. Now, we might be able to mess with some nuclei someday, but because I never want to say completely no to nothing, but it was really a leap forward in terms of our ability to control the structure of matter.
I know I'm dealing with scientists when I ask them about their lives and science enters into the discussion. One of your dogs was named Argon.
It's true.
Another dog was named Xenon. And if I'm not mistaken, if I can make this work,
Yep.
that's not your dog. It is a bump.
The man is a genius, I tell you.
It has something to do with Xenon.
It does.
What is that?
That is, technically speaking, you got it right. That is a bump. But what that bump is it's a picture taken with our scanning tunneling microscope of a xenon atom sitting on top of a metal surface. And my reason for wanting to have you see this today is several things. First thing is, have you ever seen such a beautiful xenon atom? I don't think so. No, that's it. That's the world's most beautiful xenon atom.
Did you name the dog before this or after?
Oh, yeah, the xenon was long before this.
Nice, okay.
But what I find to be remarkable, and the reason I wanted to include this particular slide in today's presentation, is it very vividly demonstrates the difference between the very small world of atoms prior to the invention of the tunneling microscope and how the tunneling microscope took those atoms and made them, instead of being remote and small and you couldn't see or interact with them, to making them big. Just look at how big that xenon atom is. On the screen, it must be huge. And that was a remarkable transition that occurred. It was really an amazing accomplishment that my colleagues at the IBM laboratory in Switzerland achieved in creating the tunneling microscope.
You have a great eye for beauty, and in getting to know you, I've learned a little bit about how you define beautiful.
Well, this is not beautiful. This is voluptuous.
Be very careful.
This is, let me tell you what you're looking at. Technically speaking, this is also a bump. What this is it's data from our laboratory taken by two of my colleagues, Suzanne and Chris, who are in the audience somewhere. And this is the electron spin resonance signal from a single atom on a surface. So what this teaches us about is the specific environment of the electrons on a particular atom, where we can see the atom, we can control the environment of that atom, and now we learn how the electron is responding to its environment, and from that, it's teaching us about the environment of that atom.
What's the significance of that?
The significance is a detailed knowledge without having to average over a whole millions and millions of atoms of the electronic structure of this atom. Why is the electronic structure of atoms important? Every time you want to use an atom to do something, to be part of a molecule, to do computation for you, or to be part of something that does computation, you've got to know what the electrons are doing if you want to be able to engineer the functionality into those structures that you would like.
Which is what we have next, because this actually does show us what electrons are doing, right? What is this?
This is something called a quantum corral. And I'm also pleased to say that the guilty party is also here in this room. Mike's around somewhere. What you're looking at is how much fun a scientist can have in a laboratory. This is also a control freak's paradise. These little blue bumps that you see are individual iron atoms. Each one is an iron atom on top of a copper surface. Originally, the iron atoms were at random locations, and we used our ability to place atoms where we want to take these iron atoms and create a circular ring, which we called a corral. And the reason we call it a corral is that on the surface, running around on the surface, are free-range electrons that are, some of them are stuck on the surface. They have to move in the surface. But when you fence them in with these iron atoms, they're stuck inside of the iron structure of this ring of iron atoms. What do electrons do? Electrons are waves. And when waves are trapped inside of a structure, they go into things called resonances, and we also call them quantum states. And these ripples that you see in the interior of the corral are a direct visualization of what electrons do when you put them inside of a circular box. So what was really exciting about this was here was one of the first direct visualizations of quantum mechanics at work. It's a textbook example of quantum mechanics at work. And not only that, but we get to shape these wave functions, to sculpt these wave functions the way we want, to see if we can engineer the wave functions to do what we'd like them to do. And the way we do that is by controlling where we put the iron atoms.
Where we put the iron atoms. You've moved atoms. What if we had the power to move millions and billions of atoms? Then what?
Then we start beginning to think about what kind of functionality we can get out of collections of atoms. How can we engineer that functionality, and how much functionality? Can we get them to do computation for us? We can ask questions like, at what level can we build things, really small things, that respond to their environment in an active way and do something useful for us? So we can think about drugs. We could also ask questions like, how many atoms, where do we need them to be in order for something to become aware of itself, or to begin to operate like a robot, or beyond a robot, to become cognizant, to be self-aware? We don't know answers to those questions at this point. We don't even know how to begin engineering. We're not at that level, but now we can imagine
Okay,
doing
so I'm going to
that.
ask, I'm going to come to Dan in just a minute, but before that, let me take the first question from the floor, courtesy of our pigeonhole, who takes, I think, this to the logical point. How will the average home life be affected or changed by nanoscience, by the ability to move atoms?
Well, we're not going to make food blenders out of this yet. I don't think it's going to immediately affect your home life. It will at maybe 15, 20 years from now, but our limitations now, the big limitation that we face, which prevents it from affecting the common person, is to be able to assemble enough atoms rapidly enough into functional structures that can be manufactured and become a technology which we can deliver into the marketplace.
But, so in the marketplace, 15 years from now, 20 years from now, close your eyes and imagine what,
I can tell you what the key element is.
okay?
Somewhere, maybe even in this room, there's a 16-year-old. And that 16-year-old is growing up in a world where there are not the kind of barriers that I grew up in. When I grew up, atoms were remote. We didn't know how to move them around. We could barely image small structures, never mind get down to atoms. Now we can do that. So some 16-year-old is going to say, oh yeah, well, if we can do that, then, and the light bulb's going to go on. I can't tell you when that's going to happen. I can't tell you the details of how that's going to happen. Maybe it's just a statement of faith more than anything else that it's going to
I
happen.
think it's a challenge to people in the room, and maybe they can be a couple years older than 16
Could be.
and still do that. Dan, let's come to you. You're here representing Calvin Quate. I think that's the good professor right there.
Yep. Yep.
And Professor joins us here,
Right.
and thank you so much. So he was your professor, right?
He was my professor.
What was he like?
He was fantastic. Now, why did I choose this picture? I chose this picture because I think it represents the way he approached science as well. This picture was taken when we were in a remote part of the Grand Canyon. And what I think it represents is kind of the independent spirit that Cal had, the adventurous spirit. He was never one to follow the crowd into something. In a lot of science, you know, sometimes there's something that gets popular and a lot of scientists move that way. He never did that. He was always very independent, and he was able to prevail against the current, right? He could find his own way. So, and I think that is really a special thing. If you want to be a great scientist, one way to do it anyway is to really think out of the box, be independent, and not just follow the crowd. Right?
He won the Kavli Prize for the atomic force microscope.
That's right.
And I understand that was inspired by a little trip he was on and some
That's
incredible
right.
work he was doing. So tell us about that and what the atomic force microscope is.
Okay, well, when I was a grad student, Cal was famous not for the atomic force microscope, but for an amazing acoustic microscope. This was a microscope that used sound waves with wavelengths shorter than the wavelength of light. And it could actually, with ultrasound, see things better than the optical microscope.
And that's what you studied on. That's what you
And that was the subject of my thesis. Cal was being honored by what was called the Rank Prize. It's a major prize given in England, and he was on the airplane. And he came across this article. There's a physics magazine called Physics Today, and I guess he was thumbing through it, and I think it was the same article that Don referred to. There's actually a very crude image here, you know, but Cal loves images. He was always fascinated by images. You know, a normal person would look at this image and say, geez, it doesn't mean anything. But Cal was really inspired by it. And he changed his itinerary when he was in Europe. He went to the IBM lab in Zurich, met Gerd Binnig and Heini Rohr, And he came back to Stanford, and there are a number of students here that will attest to this. Cal never had group meetings. We were all very independent, but when he came back from this trip, he had the only group meeting any of us can ever remember him having. He called us together and he said, we are changing directions. We are going to pursue this thing called the scanning tunneling microscope.
And that was inspired by?
And, well, that was inspired by what he saw at the IBM Zurich lab. And I think he saw something here that very few other people saw. There's no atoms here or anything like that, but he somehow saw the potential here. And so he basically started the first research group in the United States that pursued this. And this was well before anybody, they were seeing atoms or anything else.
And you were there as that shift started taking place.
So I was there. Scott Elrod, who's in the audience here, was actually the assigned to get this job going. And I had just graduated, so I had a little, but I was hanging around still, and so I was Scott's helper to try to get this thing going.
Wrong way. Sorry. What's that?
So a couple of years after that,
You were gone.
I was actually gone by that time. Cal had invited Gerd Binnig and Christoph Gerber, who was another person at the IBM Zurich lab, to spend a sabbatical here at Stanford. And they wanted to address a deficiency of the scanning tunneling microscope. Don shows fantastic pictures, but he didn't tell you that it only works when you have a conducting sample. It only works on like metals and semiconductors. And Cal and Gerd Binnig and Christoph Gerber said, well, this is a real limitation. Can't we do something that can look at other things, everyday things that are insulating? And they had the idea that instead of using a tip to measure a tunneling current, they would actually take a tip and very gently touch the surface and then scan it over and feel the atomic corrugations, the atomic forces that you get, just by taking a simple tip, but doing it gently enough and precise enough that you could actually tell what was going on. So now, of course, this was not, well, let's go back to the previous one. The reason I show this is I kind of want to make the point to the students here is that you can start a $300 million industry and revolutionize, nanoscience, starting with a simple device.
I think you have their attention now.
Yeah, so, now look at it. This is actually a replica, but it's pretty faithful, down to if you look carefully, there's some Scotch tape there holding the wires together.
And are we seeing the tip there, right at the?
Yeah, you can't actually see the tip, but what you see, these little tubes coming out on the right and the left.
And what do they do?
Those are what move the sample around and move the tip around.
Okay, and these are some of the tips that one can use?
So I said, what we're trying to do is we're trying to feel the forces as you go along. So the way this is done is you get a very sharp tip on a little spring, and you just scan it along and you watch the motion of the spring. The one on the upper left is the spring they used. It was actually just a piece of metal foil, almost like aluminum foil. It turned out to be gold foil, and they just cut it out with scissors. And then they found a diamond. I don't know whose diamond, this is, but hopefully it wasn't somebody's wedding ring or anything. But anyway, so they smashed the diamond and they glued it to this little piece of foil.
And what these tips are doing is exactly what?
And these tips are what is coming in contact to the surface and feeling the forces and being able to do this in such a precise way that they can actually go down to the atomic scale. Now, the important thing to remember about a tip is you have this tip, yeah, it's big and it looks big, but you know what? There's a final atom on the very end of it. Somewhere is the last atom, and that last atom is what interacts with the surface if you know how to do it gently enough.
One more slide, and then I want to take some questions from the audience.
And these are all the other fancy cantilevers that now you can make. They do all kinds of amazing things.
Well, what are some of the amazing things they do now?
For example, that one with in the middle bottom, that was actually used to measure the strength of gecko hairs. You know, geckos can hang on ceilings and stuff. That was actually measured the frictional force, the sticking force of gecko hairs. The one in the upper right.
Once we establish why gecko hairs are sticky, then what?
Well, then you know why a gecko can walk on the ceiling. But the one in the upper right,
Okay.
the one on the upper right there, that is actually used as a little tiny thermometer. You can actually measure the temperature. So you can actually go in on like individual transistors and integrated circuits and measure temperatures. What this has inspired is all kinds of probes, and this is what Quate's group, Tom Albrecht here in the audience was the first guy to make one, like the upper middle one. But it spawned a whole industry of making specialized probes that can measure things.
One more slide, and then we'll stand back and contemplate what nanoscience can do and take some more questions. And I'm glad to see so many are putting questions in using Pigeonhole, because it brings some great ideas and thoughts to us right here. And this is a little illustration of your work.
Yeah, this is looking again. Now, okay, we've got the scanning tunneling microscope, fantastic. We got the atomic force microscope, also fantastic. It can look at all kinds of different things. But you know, there's one problem with both of those. They only look at the very top surface. Mm-hmm. I wanted to have a microscope that can get the kind of atomic resolution that these guys are getting with the AFM and the STM, but actually look below the surface.
Toward what end?
Well, the big application, if we could ever get there, and we haven't gotten there yet, would be able to take molecules and see the three-dimensional structure of molecules. And this is important because if you could do this with proteins, then you know, proteins are the basis of life. It's the basis of you know, the pharmaceutical industry, making the right kind of chemicals with the right structure. And the way proteins work, they're like little atomic machines. And to really understand how they work, you need to know the three-dimensional structure. So this is still hasn't come to fruition totally. We've been able to, for example, this is a magnetic, what it's trying to do here, we're trying to do magnetic resonance imaging, MRI. You know that from hospitals. Sure. Well, you know, MRIs are amazing because they can look inside your head, right? That's what we're trying to do here. We're trying to look inside of molecules, and the way we're doing it is we're using some principles from the atomic force microscope. We have a cantilever, and we're trying to measure the magnetism. There's a little magnetic tip, and we're trying to feel the magnetic force from the object, another spin in this sample, another magnetic object. But we're trying to do it super sensitively. So this little cantilever I illustrate there has a sensitivity that's 1,000,000 times more sensitive than an atomic force microscope. And
That's crazy.
yeah.
I saw him do this.
So
It's crazy.
anyway, this is a work in progress, you know, whether it comes to fruition or not, but it has I think a very nice goal of really trying to do what Don has done and what the other STM guys have done, and do it in 3 dimensions.
I will go to some of the audience questions in just a minute, for a few more minutes before we move to our next panel. But before we move on then, coming back to Calvin Quate, who I believe is 94 years young, is that right?
That's right, still going strong. I'd like to point out he learned how to windsurf at 65, so.
Okay, well,
so,
that's great. Well, that's inspiration to us all. But how would you then capture the impact that his work has had on those of us in this room and on this field?
Well, the atomic force microscope has become the workhorse for many fields. The STM is a little specialized, but the AFM, we have like 5 of them in our laboratory. And what do we look at? Well, the most common application is looking at, say, semiconductor devices, just the structure of things. But I wrote to another one of Cal's students, Sungil Park. He actually is he owns a company which is a major manufacturer of these microscopes. He says, well, Coca-Cola uses the atomic force microscope to look at the coatings inside of Coke cans. Gillette uses the atomic force microscope to look at the smoothness of razor blades. And the other one, which I thought that was the most fascinating, was L'Oreal uses it to look at the structure of hair, the texture of hair, and then they can evaluate what their conditioners do to the structure
Nanoscience
of
will
hair.
bring us better shampoo.
Yeah, that's right, absolutely.
All right, so let's get to some questions from the audience. Can you build 3D structures from individual atoms?
Just barely. Though, at least the way we're doing it, it's always been difficult because that requires not just sliding them along, but picking them up and assembling them. And you can't just put atoms any place you like. They've got a bond in that configuration. That's one of the big challenges, is to not only learn how to build out, but to build up.
What, if any, are the ethical issues or dangers nanoscience has the potential to raise, or is it all upside? Is anything all upside?
I don't think nanoscience is any different from any other science or any other human endeavor. Every time you find out how to do something that you couldn't do before, there's probably a beneficial application of that, but if you are so inclined, you can also probably find something not so good to do with it.
I would just like to say that early on, I mean, there were some, questions raised, like, whether there are going to be little nanobots, going through our bloodstream, and, these things are very far out. I mean, this is,
You worry about that?
No, I don't worry about that. I think a lot of the dangers were overblown. Now, but, I mean, a lot of nanoscience does deal with, particles, small molecule particles. And just like any chemistry, you have to be careful with that. I mean, I don't think it's...
Another good question from the floor. What are ideas in the medical field where nanoscience might be helpful? The medical field. I know there are a number.
I know my colleague Naomi Hollis at Rice University, was working on these gold shells that were nano size and could be delivered to cancerous tumors. And then they could be heated with infrared light, and they would soak up the infrared, get hot, and use that heat to kill the tumor. That's just one example I remember from many years ago. I think the number of opportunities for applying the knowledge that we develop doing nanoscience to dealing with medical issues is phenomenal. I'd love to have a new piece of cartilage right here, and right there in that knee. But finding a material which can really work well as a synthetic cartilage has been very tough. Our cartilage is really remarkable. If you wanted to solve that problem, what would you do? You'd want to understand how surfaces wear at the atomic level and see if you could engineer systems that would be strong and durable and wouldn't wear. What tool would you use to get that job done? Cal's atomic force microscope.
Anything to add on the medical front?
Well, I'm interested in tools, and so tools that allow you to really get down to the molecular level is really key to understanding. Most diseases have a molecular basis, and so any tool you have that you can bring to bear to that.
I'm going to end with this last one. Where can school children learn about atomic force microscopy?
Actually, yeah, Stanford, there was, for a number of years, Stanford had a very nice NSF-funded program on nanoscience and on scanning. We call it scanning, what do we call it? We call it probing the nanoscale. Mm-hmm. And they explicitly had a summer program for educating middle school teachers in the wonders of nanoscience. And we give tours all the time at IBM to school kids.
I think I recall that some high school student in the Midwest built quite a nice functioning atomic force microscope. Just sort of all in there. They're not, once you know how to do
They're
it.
actually not that hard to
not
build.
that hard.
You know, you can make it look like that old one.
I would
so.
prove that wrong, actually. I think it would be very hard to
You just need some Scotch tape.
Trust me on that. Just some Scotch tape.
Yeah, duct tape.
I'll hold you to it. Would you join me in thanking our panel here and especially join us in thanking Professor Quate. Thank you very much. So our next panel, and I'd like to invite them up, we're going to go from nano to neuro, I think. Whoops, I don't want to give that away. And I'd like to invite our next panel up. And Michael Merzenich is Professor Emeritus in Neuroscience at the University of California, San Francisco. Carla Shatz, hello. Professor of Neurobiology and Biology here at Stanford University. And Richard Scheller studied chemistry and first as undergraduate, then his PhD at California Institute of Technology. So have a seat, everybody. We're going to go from really tiny things to really complicated things, like the brain now. Thank you all for being here. This is just really great. And congratulations to all of you for being laureates here. I want to talk to you each about that very, very briefly. So if I could do that. Kavli Prize for?
Neuroscience.
Yeah.
Brain plasticity.
For brain plasticity,
Right.
which you shared for brain plasticity.
Right.
You're coming at us from the auditory, and right? Among other things.
Everywhere.
Everywhere?
Right.
And you're about the eyes.
I'm about the eyes, and I'm about plasticity during early development, because I always want to know why kids can learn things like languages so easily, but we can't.
And Richard, 2010 Kavli Prize for?
I'm a molecular biologist, and we figured out, along with the other laureates, how nerve cells communicate with each other at a very, very fundamental level.
And you're now at a place called 23andMe. Anybody heard of 23andMe? All right, I have. My son gave me a little thing that I learned all about myself, which I don't think I want to share with anybody else, but I've already shared it with you. So you've got all that data, and you're doing what there now?
Well, at 23andMe, we look at the differences between individuals. You all know in your DNA, you all know your 3 billion bases is your genetic code. We all differ from each other by about 4 million differences. To put that in perspective, we differ from a chimpanzee by about 10 times that amount, by about 40 million differences. And it's those differences that are in part responsible for our traits. We can figure out a lot about your ancestry. We provide a report that tells you if you are a carrier for a particular set of genetic diseases. And we're also able to tell you whether you are at an increased risk of developing certain diseases, such as Alzheimer's disease, Parkinson's disease.
So you can actually see the markers.
Yes, yes. And, you know, it's quite a controversial company in a lot of ways, because there is no physician involved. You can go stop on your way home at a drugstore and buy a kit. You can go to Amazon and buy a kit.
Mine
You
came
can
in the
go to
mail.
our website and buy a kit. And we also, for example, we know many thousands of women that are mutated in the BRCA gene, so they have a very, very high risk of developing an inherited breast or ovarian cancer. And we are currently in very productive discussions with the FDA, but at this moment in time, we're not able to tell them that they have this genetic marker.
So talk about ethical issues, right?
Yeah.
We'll come back to that and to all these things. Carl, let me start with you. Watched your TED Talk. Love your TED Talk. I especially loved your reference at the top to your grandma and the role that your grandma played in getting you involved in something you call making the old brain young again. Tell us about your grandma.
Well, thank you, thank you. Well, my grandmother was an amazing person. Came from Russia. She actually was the first person in our entire family to go to university. And tragically, she had a pretty massive stroke when she was, when I was just beginning in college, and she was elderly at that time, but still had been all there. And I just will never forget that we used to go visit her in the was really a rest home at that point. No rehab, the idea, the concept that you might really be able to recover function and retrain, that wasn't there. So she was in her wheelchair. And my wonderful uncles, both of whom were neurologists, could exactly diagnose where her stroke had been, but couldn't do anything about it. So I resolved not to go to med school. I thought we needed to know more about the brain, and in particular, really more about what makes the brain able to change with learning and experience, and wouldn't it be wonderful someday to be able to go back, maybe even with a pill, and give the pill to my grandmother and have her be able to recover function, because she was not able to do so at the time.
So you dedicated yourself in many ways to your field because of that experience?
Well, I would say, because we're really talking also about useless knowledge and how wonderful it is, that I also was totally fascinated by the brain, and I wanted to really understand how it wires during development, all the circuits and so on. So I think it was the extra stimulus that made me decide to really become a scientist as opposed to becoming a clinician, because I felt like we just didn't know enough to be able to treat her at the time. And then I think just the beauty of studying the brain really captivated me for many years, and I never imagined we might get to make the pill.
Well, we're going to come back to that in a minute, because you're doing something with mice that just may, who knows, one day. But let's go to your work for a minute and the discovery that you made about how our eyes and brains are connecting in utero, which was a gigantic breakthrough.
Oh, well, thanks. I mean, so I learned all about the connections between the eyes and the brains, and they're so precise. It just seemed as if nothing could be left to chance. It all had to be controlled in a very precise way, hardwired. But we already knew that, in fact, your brain has to learn how to use both eyes together during a postnatal period of life, during a developmental critical period. And yet it's known that so many connections form before birth, as you said, in the womb, so in utero. And so it had just been assumed that all of these connections that form early on must be hardwired, because, especially in the visual system, because there's no vision in utero, obviously. And we started to study this, and we were just very surprised, first of all, to find that the adult pattern of connections is not present initially in development. And there's a kind of,
The adult pattern of connections is not present initially.
So the eyes normally make certain connections and circuits, but those connections are actually not quite sharp and precise initially in development. And there's a period where the connections, the synapses, actually remodel, and that remodeling involves strengthening of some connections and weakening of others. And so, but this is also known to happen after birth, and in that case, vision and using your brain is what causes the remodeling to happen, and actually Michael has studied this in great detail after birth. So it was thought that this same mechanism of use couldn't happen in utero. And the big discovery we made is that the brain actually runs test patterns on itself early in development. And even the eye is sending signals to the visual part of the brain, and those signals are kind of test patterns that are being used to test and remodel the connections in a very similar way to what happens after birth with vision. And actually, at first, people didn't really believe this could be true.
Right.
But we discovered even how the eye does this. And we looked at these beautiful patterns that were sent from the eye to the brain in order to do this kind of tuning up and pruning and strengthening of connections.
Is that a beautiful pattern?
That's it. That's sort of a, that is a real experiment in which we were looking in the eye, and every color here is a group of thousands and thousands of nerve cells in the eye, and these cells all become active and start to send test patterns to the brain together. And actually the different colors are in time. So dark is initially and light is later. So you can see these are kind of like waves. There's a purple wave, then there's a blue wave, then there's a red wave. And so hundreds of thousands of nerve cells are sending actually correlated activity to the brain, and this is all spontaneously generated in the fetus. And this was a big surprise to everybody because it had been thought that this kind of activity really wasn't present, but after we found it, people found it also in the auditory system, in the spinal cord, in the somatosensory system, and so on. So this idea of spontaneous activity, testing sort of almost like in preparation for later vision.
I should say that in addition to being a remarkable scientist, you are also a remarkable poet. Cells that fire together, wire together. Out of sync, lose your link.
Thank
Is there
you.
another verse to this?
Would you like to suggest one?
No.
You got me.
I'm not going to, but I am fascinated by this and the work that you've done both to block some of this signaling, receptors involved in the synapses that you've, and these experiments that you've been doing with mice, back to the pill again.
Yes.
So why don't you tie that together for people?
So these little ways of, this is for good for teaching and remembering the idea that, in fact, when nerve cells all are firing and working together, they actually strengthen their connections. And those connections that are not active at the same time are weakened. And this was a postulate many years ago by a famous man called Hebb. And now we know this to be true, not only in the development of connections, which is what I study, but also in areas of where people study learning and memory. So these connections are really strengthened with use. It's kind of like, what your mother always told you, is a use it or lose it thing. So that's what really is happening here. But then my lab, and I have to say hi lab because many of them are here today. I'm so glad to see you guys. We became very interested in how could neural activity ultimately be turned into a structural change in the connections, because I told you that this early testing of connections really makes some of them remain and others are pruned away. So we made many experiments searching for molecules that might be important for the strengthening or weakening of connections during development. And we made another rather unexpected and controversial discovery, which is that a set of molecules that are normally used in the immune system and were thought really to be the major purview of the immune system, important in the kind of adaptive immunity that we have that prevents us from getting a heart transplant, for example, unless it's the right type of sets of molecules. These are called major histocompatibility molecules. But we found that actually the neurons are using these molecules too. And they're using them for this decision-making and for pruning of the connections.
So let me put this up.
Sure.
The pruning.
The pruning, yeah. So, and I mean, the thing that was funny about this at first, and not so funny to us, is that the immunologists, our colleagues, didn't really want us to have these molecules in the brain. So we had to do many experiments.
What do you mean they didn't want you?
Well, because they were found first in the immune system, and they were so important in the immune system, no one had ever seen them in the brain, and so people thought they couldn't possibly be there. So we had to work for many years to convince everyone that the molecules are really there. And this is just a pretty picture showing a number of these famous MHC class 1 molecules actually in the brain, in the neurons. They have different colors. And in fact, we're really working hard to understand how they work in the neurons.
The connection of this pruning to autism or Alzheimer's and the work that you're doing now is utterly fascinating. Could you tell us about that?
Well, the word pruning, so the idea is that connections are formed, and then if they're used, they're strengthened, and if they're not used, they're weakened. And I think many of you know that memories are stored at these synapses, these connections. So if you lose connections, if they're accidentally pruned away, this is not a good thing for memory storage. And we realized in the developing brain, we could understand something about this pruning process, and we even could understand something about molecules that are involved in pruning. So we wondered whether that might have relevance to Alzheimer's, where the first signs of Alzheimer's really well, eventually you have serious memory loss, and at first you have maybe cognitive, mild cognitive loss. And it's possible to study Alzheimer's in a mouse model, quite a number of mice models. It's possible to take, as Richard mentioned, we know that there are some genetic causes for Alzheimer's disease, early onset Alzheimer's, and sadly, those genes that are mutated for early onset Alzheimer's can be put into mice, genetically engineered into mice, and then the mice also get Alzheimer's when they get kind of old. And so it's possible then to study Alzheimer's in mice, and when one does that, one finds that early signs of Alzheimer's involve too much pruning. And we discovered that our molecules seem to be playing an important role in the pruning process. Not just these molecules, but they have receptors. These MHC class I proteins have receptors that actually transduce the signal from these proteins and tell nerve cells to prune away their connections. And when we realized that, we actually could, in the mice, by blocking these pruning receptors, we could prevent the mice from getting memory loss and Alzheimer's.
Hang on, let's hear that again. So you can prevent the mice from getting memory loss,
yes.
Right? Which is pretty amazing.
It's pretty cool. So wouldn't it be nice if we could apply this knowledge to the human condition?
Right, and?
We're looking for the human genes that would be the analogous genes to the ones that we're studying in the mice.
You've also got to look at the downside too, because what we don't know is if you do that and you encourage growth of the synapses, could that be offset elsewhere and affect memory loss?
Right. Well,
elsewhere,
you might actually be able to encode new memories, but you might actually lose old memories. So there's quite a lot of work to be done. So I would say that actually we can give this pill to mice. It seems to protect them from memory loss, but whether I would take the pill, not yet.
Okay. Michael, I'm not going to ask you, how eager you are to take the pill, but I am going to ask you about the plasticity of the brain from how you're coming at it through auditory. So where did that come from with you, and how does that, you shared this, the Kavli Prize, how does your research support or differ from what we just heard in terms of plasticity?
Well, we conducted research in two other great brain systems, in the somatosensory system and in the auditory system. And we realized in the mid-'80s that the brain was continuously plastic. We could demonstrate that each time you acquire a skill or ability, you account for that acquisition or improve any ability by again, brain remodeling. You're actually changing the connectivity of the brain. You're actually changing the brain in a variety of other ways.
Brain remodeling, what is that?
Well, you're actually changing brain systems so that they now support, you could say, the acquired ability. You could progressively refine them. You progressively specialize them. And that specialized circuitry supports every dimension of the new ability.
Some of your early work dealt with a cochlear implant, and you learn things in
Right.
that. And I think that would be very interesting for people to hear because it seems to certainly support your...
Right. It was wonderful that I was a faculty member in a surgical department, actually an otolaryngology department, as well as in a physiology department. And there was great interest in hearing and hearing loss. And I actually led a team of scientists and engineers, medical doctors, that created what became one of the commercially developed cochlear implants. And as we applied these devices, the whole notion behind a cochlear implant is to, in a deaf individual, is to shock the auditory nerve with pattern stimulation to simulate the normal input that would be delivered by sound, for example, the sound of speech. And our notion was that if we could be precise enough in that translation and engage the brain and shock the auditory nerve, the hearing nerve, then maybe speech could be intelligible, speech could be learned. And not surprisingly, when we first applied these devices in profoundly deaf people, they described what they heard as being noisy, uninterpretable, like a language of a robot. I mean, after all, our simulation was very crude. I liken it to playing Chopin with your fist. But not too many weeks later, they heard everything. And they actually received speech with high intelligibility or high reliability. And as we were patting ourselves on the back saying, wow, this is amazing, across the world were two other groups, one in Australia and one in Austria. And they had completely different ideas about how to make this translation of the sounds of speech by shocking the nerve. We thought they were crazy, but it turned out the brain didn't care. The brain took these very different forms of input. We replaced the primary form of input delivered from the ear to the brain, and it's capable of constructing intelligible English or German or Australian English perfectly nicely and make sense of it. And that can only be accounted for, and we now know it is accounted for by massive plasticity. In individuals of any age, you can apply one of these devices, of course, into an 80-year-old, and they can acquire speech up to a high level within a few months of the use of their new device. Their brain has amazing powers of change when it matters to it.
So here's a slide here.
Yeah, right.
That where you've been actually tracking this. Tell us what we're seeing and what is developing.
Well, actually, I chose this slide because the research that's shown in the slide was conducted at Stanford. And actually, the children that were involved in this study were from a school about 10 miles from here. And this is just to illustrate the fact that we massively specialize our brain across our lifetime. The operational person that you are has been a result of this change on a massive scale that's occurred. Quadrillions of moments of change define you, define the operational person you are. And one of the modern abilities we humans acquire is the ability to read. Most of us in this room, probably everyone in this room, has acquired this ability. And when you do, you acquire a reading brain. You can look down on your brain, which is the brain of the reader, and you see patterns of activity. You see the brain is engaged in a way that accounts for the reading. So this more posterior area that's highlighted in green is the area in which the fundamental translation between the sound parts of words that bear meaning and their representation by written script is occurring. So this is the hearing to visual translation zone. And the area to the left, the activity is strongly correlated, correlation coefficient about 0.85, with the ongoing interpretation of the meanings of words that are being received from written script. So in other words, we can look down in the brain and we can account for how these alterations, how these distortions account for the improvement of this ability. Of course, a kid that can't read lacks a reading brain. It turns out that we became very interested in driving brains correctively in older children to see if we could recover restore the brain to more natural operations. And so we've trained children in this particular study at Stanford, millions of children across the world. And very rapidly, by intensive forms of training, you can provide the child with the gift of reading.
Let me move on to this next slide because.
Well, before you do that, I just want to say.
Okay. You want to stay now?
I know I'm taking too long because I talk too long and too confusedly. I just want to say that as a consequence of this, children acquire a reading brain, and about 85% of children within a few months after the end of this training are reading at a grade level or above. I just want to say that none of the training is in reading. All of the training involves listening training, because the reason most children can't read is because of problems in listening. And that's another way of saying you need to understand the neurological basis of ability and disability in order to try to use these tools to drive correction to help people that struggle.
Let me quickly go through this, because in the training that you do, you started companies and you actually do this brain training.
Right.
And you've conducted experiments on these things.
Right.
tell us what you found.
Well, I've just chosen an example from an individual that's an exceptional individual. So this is a business executive from Australia, and here his brain has been trained, and it's been trained in ways that drive improvements of the speed of operations of his brain. And you can see that reflected that before training at this 100 millisecond benchmark in his visual cortex, there's no activity in this particular attended visual behavior. And then after he's trained, there's strong activity. And in fact, he's responding in his brain about twice as rapidly. And the whole activity sweeps across his brain at high speed after training as opposed to before. And in a variety of ways, because we know that half of the variation of adaptive intelligence is actually accounted for by brain speed. The task at the right in this business executive, this is the difference in a task which index adaptive intelligence. Everybody is improvable. Everybody is a work in progress. Every individual on the planet. And you basically drive improvements of their brain that will make a substantial difference in their performance abilities. Your brain is continuously plastic.
All right, so then you both are on the plasticity thing, and this actually tells us if your brain is continuously plastic, you've worked on telling us here that across age, we retain plasticity.
Right, well, we've trained individuals at every age with a rich variety of neurological problems, children and adults. And all of these studies are designed to address the specific limitations that they have neurologically to use our understanding of the rules of plasticity to engage their brains to drive them in strengthening and corrective directions. And this is a simple example of driving improvements in what we call processing speed in the brain. And this is how rapid the brain can operate, again, to make rapid, accurate decisions. And this is a critical skill and ability because it actually reflects fundamental brain health. The reason it does is because a whole series of chemical and physical aspects of brain function have to be operating in high fidelity with high resolution in good health in order for the brain to operate at high speed. So when you drive improvements in processing speed, you're driving improvements in organic brain health.
And what this shows us, if I remember your explanation I'm reading right, is the untrained brain at age 20 is operating at roughly the same
Speed as the trained brain.
the trained brain at 65, at 70.
That's actually 75. So in other words,
I find that the most encouraging thing I've heard in a very long time.
yeah, well, yeah, actually, of course, if you train the 20-year-old, they're still superior. But you can keep training the 75-year-old. By the way, I'm 75.
Are you training your brain?
I can get.
Are you training your brain?
Yes, I am.
Okay.
And I'm pretty close to the average 20-year-old that's trained. So think of that. How scary is that?
I find it not scary, but totally encouraging. Richard, let me come to you, and we've got a ton of questions from the floor because everybody has a brain and wonders about how they're going to do. You talked a moment ago about this ethical issue that you confront. You have a massive amount of data now at 23andMe. What does that offer to us? What does your training tell you we can do with that? We promised to talk about the future here today. I think that holds incredible implications for the future with what you're sitting on.
Well, we have over 5 million customers and over 1 billion data points on the phenotypes of the customers. And all of this data is self-reported, but self-reporting data is really quite an amazing thing. For example, we ask people, are you a morning person or an evening person? And they tell us yes, no. And then we look at the genes that are enriched in morning people versus evening people. And what do we find? The genes that underlie human circadian rhythms. So with a very simple question about your behavior, we're taken to the genes that regulate this behavior. We don't even define what a morning person is in this question. You define it for yourself. So it's really quite remarkable, and what I'm attempting to do is to sort through all of this data. We, of course, ask people about any diseases that they might have. And so, for example, have you ever been diagnosed by a physician with, pick your favorite disease, psoriasis, arthritis, what have you? And we find genes that are present at different frequencies in folks with the diseases versus the controls, people without the disease. And if this is all statistically significant, that means that that gene, or that variant of the gene, must have something to do with the disease. Otherwise, why would it be present at a different frequency in people with the disease versus people without the disease? Then this gives us ideas about how we might make new medicines to help with these diseases.
How does the trove of data that you're on and some of this help the work that they're doing, because you're working with genes?
Well, for example, I think it was last year, perhaps the end of the year before, in a collaboration between 23andMe and some scientists at the drug company Pfizer, we were able to publish the associations of a number of genes that are involved in depression. And this was the first study where a genetic link to sporadic depression was ever seen. We have sadly, hundreds of thousands of people in our database that report that they have experienced depression. So again, by knowing the genes that are involved in these types of conditions, we get ideas on how we might be able to generate therapeutics or perhaps other ways of intervening in these diseases.
Are you working actively together in this way?
Not with the two people on the stage, but the 23andMe does collaborate with
Maybe we could get something going
with
here.
tons of academic scientists. Actually, we have we're a small, non-profitable company. We have many more requests than we're able to handle in terms of collaboration.
Richard, come back to what you talked about earlier, which is difficult and fascinating, which is the information that you have about people and what their genetic codes could tell them about their futures or probabilities, and what you're able to do with that information, and how that presents an ethical dilemma, or does it for you?
Well, sure it does, because for many years, 23andMe provided a health report to people, and before I joined the company, received a letter from the FDA telling us to stop providing this information to people and to discuss this with the FDA.
And what was the information that people were getting?
Information about your health risks, for example, Alzheimer's disease, and a gene called ApoE4, for some of you might be experts, or your risk of getting breast cancer for a BRCA mutation, the famous Angelina Jolie mutation, your risk of getting Parkinson's disease, and so on. And the FDA wanted, I think rightfully so, for us to be able to demonstrate two things to them. First of all, the analytic validity, that the test we ran essentially works. And then this was pretty novel, and this was never really done before. They wanted us to demonstrate that the report that we were provided to people was comprehensible. So we actually write a report, we give it to people, they take a test, and they have to score pretty well on the test, and then we present that information to the FDA, and they're now approving our health reports so that we can bring them back to folks that we believe we call our customers.
Are you completely comfortable, and do you believe that the information that you have and gain should go to every customer and every person, whether they ask for it or not?
No, we have to ask for it. I mean, I don't believe that any of this information should go to anyone that doesn't want to see it. And it's perfectly possible to go into our website and say, I want to know where I'm from, I want to know why my eyes are blue, but I don't want to know if I'm going to get Alzheimer's. So no, we would never provide anything to anyone who doesn't want to know it. I know. I took the test.
Okay, I won't ask. Would you want to know?
It depends on the outcome of the most current clinical trials for drugs that treat Alzheimer's. I'm waiting. I haven't taken the test yet.
Do you want to know?
I think that it should be, and it will be, a general requirement that that medicine knows. You know, your doctor should know, for sure. I mean, 5% of the human race is at risk, serious risk, for the onset of Alzheimer's disease, 20% for substantial risk because of genetics. And I believe that Alzheimer's disease in most of those individuals is probably preventable by driving the brain in a corrective direction from a relatively young age. I mean, we can have very substantial improvements in brains by intensively engaging them in appropriate ways from a young age.
You agree with that?
No, I don't agree with it, but I mean, I think it's a very hopeful concept and needs to be proven.
Right, but in any event, you should be beginning at a young age to challenge your weaknesses, right? And any vicissitude that might lead to a bad end.
I have
I have a funny story, if I could interrupt.
Always like funny stories.
No, there really isn't that much one can do once you started to show the signs of Alzheimer's disease. So, you know, many people generalize this to say, you know, there's just nothing you can do. So I was in on a Sunday morning once at Genentech with a famous scientist who was in the lab next to me. And we used to give away DNA sequences as prizes if you'd come to my town hall. You know, but you had to be there. So I said, so, you know, Napo, did you put your name in to, get your DNA sequence? And he said, no. I said, well, why not? He said, I don't want to know about any of these things where there's nothing you can do. And I said, well, what do you mean? He said, what if I'm going to get Alzheimer's? What could I do? I said, well, you can stop coming to work on Sunday.
Right? Take a longer vacation.
Which he never would have considered.
So I want to go to the questions from the floor. And for those of you who are following along, see the top question there. And I'm going to ask Carla. Before I ask Carla the top question, drum roll please, I will observe that you became the first woman to gain a PhD from the Harvard Department of Neurobiology in 1970. The day before yesterday. The question is, what challenges have you faced being a woman in STEM?
She also then became chairman of that department, by the way.
First woman.
And the moral there is that you should always be really nice to your students because someday they might be your boss. I mean, I think there are many challenges facing women. I mean, I think we all noticed even tonight that there's only one woman's face up on the Kavli, and I'm very honored, of course, to be that face. But I think part of the challenges really have to do with different styles of doing science and then how that work is recognized. And I think it's interesting that, for me anyhow, one way that I maybe dealt with being a little bit on the outside and not in the inside, since pretty much everyone else was a male and all of the professors were male at the time, was to really work in peripheral areas and to ask questions that didn't require me to to immediately compete with everybody else in the world. And I mean, I suppose the irony is then you make a really big discovery and then you create your own competition, but that's actually a wonderful thing. So I think that's part of the challenge, is that you work rather outside of the lamppost for a while, and people keep telling you that you're wrong or they don't believe it or whatever, and that requires that you have a lot of faith in yourself and your ability to prove that you're right.
One of the most amazing interviews I had an opportunity to do was with Sandra Day O'Connor, and she told the story of being a woman trying to make it into the legal profession and having all the men, and that's who was all around her, saying she'd be a great paralegal. that this was not something that a woman could do. Did you confront that?
Absolutely.
Or an equivalent of that?
Yeah, but I mean,
Did people tell you that you were wasting your time?
No, because I had really wonderful mentors, and they were all mentors too. But they were really wonderful. But I mean, this is sort of a joke, but it's serious. I think that all of us, and Arvin is one of my contemporary as well, I think a very important thing that we all had to think about was how do we dress to go to work? Because I have to say that when I started my lab at Stanford and I was in the lab working all the time, everybody would walk in and they would look at me and they would say, "Where is Dr. Shatz?" So, you know, you really have to think about how you project yourself as well as the work that you do.
Have a lot of young women from your lab here. Is this still an issue?
I don't know, we'll have to ask them. It's not as bad, but I think we're all still aware that we have to think about how we project ourselves.
Next question. It's fascinating. We could have a whole conversation about this. And let me just say, I'm pulling for you here because I have a daughter who's University of Hawaii, which is not a bad place to be as long as they're not aiming false alarm missiles at the place, who's studying marine biology. And we need to have a scientist in the family who's going to go far. And maybe we can get some mentoring going on here. Another question, Dr. Merzenich, how does the same training that recently was shown to delay or prevent dementia also help Tom Brady win the Super Bowl?
Well, that's a good question. Well, it helps anybody that can use it. And actually, it helps a rich variety of individuals that struggle from birth, more or less, to the end of life. Because your brain can be stronger no matter what your vicissitudes. So we're actually applying it to address a wide variety of conditions, psychiatric illness in many forms, and many things that happen in a life that basically degrade the quality of life, acquired impairment of different classes that can be substantially addressed by basically intensively engaging your brain to drive it in a renormalizing or strengthening direction. So Tom Brady can be faster. He can release the ball a little sooner, a little quicker, because he can see the players in front of him, and he's trained with our programs, and he swears by them. He also says he makes many fewer mistakes following Coach Belichick's directions, because he can remember the complex plays and can call the plays, making many fewer errors. So he's an advocate. You know, I just talked about a brain executive that could be trained. Well, this man, after training, came in 53rd in the world in a memory contest in England, in a world contest of memory ability.
But is this anything different than just like, you know, if somebody, you know, does crossword puzzles all the time, they're going to...
They don't work, alas. And one of the differences that what's happened in this science is from the core of the science. These are not cognitive training exercises. They're not training about human ability. You're not practicing to remember. They're all about changing your physical and functional brain. They're all about changing the core process in the brain that support all elementary and also all complex behavior. So this is brain training. This is different. This is engaging the brain to change itself physically.
Carla, there's a question. Can you say more about pruning for teenagers and whether there may be treatment for teens who struggle with autism?
Well, autism is a huge, challenging problem, obviously, and some forms of autism are, again, known to be caused by specific genes that in mouse models, I mean, how do you study a mouse with autism? But you can give mice the mutation, the gene mutation, and then you can study the cellular basis in the mouse brain. And when you do that, some of these genes actually are known to affect the process of pruning. So a hope is, again, that if one could understand exactly how these genes function normally, it would be possible to somehow restore the pruning process to normal. Now, to do that, I just want to say to everyone out there who is really thinking about, you know, their own research challenges in the future, the problem is, how do you study the pruning of synapses in the human brain? The scale is an enormous problem. This is going to be a marvelous discovery by perhaps a combination of nanoscientists and neuroscientists to somehow reduce the scale of studying the human brain non-invasively, so we could literally see the synapses that are present in the brain and see them change and diagnose at the level of synapses rather than at the level of behavior. So we could go with Richard's with the genes, and we could really look at the synapses, and we could literally see the changes that happen. They wouldn't just be red blobs in the brain. They would be real connections.
Richard, question for you. Should 23andMe's data be freely available to the scientific community?
Much of the data is, although some of it isn't. We have, we are a for-profit, we are a non-profitable for-profit company. So, we have to withhold some of our data to exploit for our own purposes. But as different versions of the data set, after we look through different versions of the data set, we do generally make it available to people. And as I said, we have, I don't even know how many, probably scores, maybe 100 academic collaborations where we are working with folks and publishing papers to make the data available.
We need to move to the next panel, but one of the purposes of these conversations that we're having here really is for us to help imagine where the excitement in the field is in the future. And you've all touched on this, and I think it's something that everybody in the room thinks about or should think about, no matter what their age or what their background is, and that is this notion of how our brains age, how much plasticity we really have, whether something can be done to intervene, to stop, slow, cure Alzheimer's. And I'd just love to invite each of you to offer your thoughts on where you think that future in that research is going to take us. And are you optimistic, based on what you know, that this is an area where there can be significant progress, perhaps leading to that breakthrough moment that we would all imagine and dream of? And Richard, you want to start with that?
Well, of course I'm optimistic. You can't be a scientist without being optimistic, because science is tough. Everyone who's a scientist here knows most experiments don't work. Your hypotheses are wrong. So you have to be sort of a generally, I think, optimistic person to come into the lab every day.
So where's this going?
So of course I'm optimistic on the one hand. On the other hand, I think it's been very the studies on intervening with Alzheimer's disease over the last 5 years have been extremely disappointing. I think we know the cause of the disease. There's human genetics that is so sound. You make more of this, you get the disease early. You make less of it, you get the disease later. It's not even complicated. But to intervene is, in a mechanism of intervening, it has been extremely difficult, and there have been billions of dollars spent, and all of the clinical trials have failed. So we just have to stay optimistic, double down. We will find ways to intervene, but it's tough.
Michael?
We already know from a controlled trial that we can delay the onset of dementia in elder populations. We have a massive amount of information that demonstrate how the brain changes progressively beyond its basic neural function, how it changes in supporting itself with its vasculature and its intrinsic immune system and so forth. We know that the system that protects the brain from agents in blood is plastic. We know that we can engage the brain and train it and reconfigure a youthful fidelity, a youthful organization of it. The brain is massively plastic, and increasingly we see an evolving medicine in which we'll manage brain health. And when you go to the doctor will basically do simple things with simple assessments in blood and in behavior that will inform you in general about the state of your brain health. And then we'll do something all across the life. And when we get to that, we will prevent not just the onset of dementia in the majority of people that now fall prey to it, but a rich variety of other conditions in the psychiatric and the neurological realm. This is in our future, to my mind, with certainty.
Carla, we started by talking about your grandmother.
I forgot what I was going to say. No. I don't know if I'm as optimistic as my colleagues, because just think of it. In the case of Alzheimer's, the disease-causing genes and even the disease-causing proteins that are known to be associated with the disease, we barely understand what their normal functions are. And their normal functions actually begin, many of them, in early development. So I think, I think this is both the optimistic and also pessimistic. I think we will learn much more about how to treat some of these diseases by understanding not the pathology only, but also the normal function of the genes. And to do that, we're back to discovery-based science. We're back to, just science for its own sake. And I think that is at risk right now.
At risk?
At risk.
Why do you think
I
that's
think it's at risk in the context of our, as you mentioned, and as Bob Conn mentioned, in the context of current attitudes about really supporting knowledge and supporting truth and discovery and about funding issues. I think we all have to really be very aware and be very active about telling the story, not only about the clinical challenges and all of our personal challenges, but also about the real huge importance of fundamental discovery.
Well, I need to follow that up because, when you and I were talking a while ago, we were talking about the Pfizer decision to get out of some of this, and you mentioned it just a moment ago. So is that something that should be very worrying to us, or, in terms of this research that needs to be done? We've got government on one hand, we've got the private sector on the other.
Oh, there are plenty of companies that are very interested in neuroscience. I think that the Pfizer decision is too bad. But look, I completely agree with Carla. We have to support basic curiosity-driven research. That's where the discoveries come from. As we learn more about the brain, Pfizer will be back, believe me. But it all depends on the government funding and the Kavli Foundation funding basic science.
That is a great place to end this discussion. You'll be around and we can pick your brains, your plastic brains, in the future. Thank you for the encouragement. And we'll make the move. Thank you so much. It's great. Thank you. All right, last panel up, and we're going to have a quick conversation. We're going to go from brains to space here. And this one I'm very much looking forward to. And after this, we're going to have I'm going to turn it back over to Ule, and we're going to have a great opportunity to take a break. But join me. And let me introduce panel. This pigeonhole seems to be working well. I'm enjoying your questions very much. It seems that that's working for you all out there, so that's good. Let's start with Michael Bolte. He received his PhD in astronomy and astrophysics from the University of Washington in 1987. Held a Plaskett postdoctoral fellowship at the Hertzberg Institute for Astrophysics and was selected as one of the initial NASA Hubble Fellows in 1990, and that must have been unbelievable. Just unbelievable. In 1993, became faculty member of the Department of Astronomy and Astrophysics at the University of California, Santa Cruz, served as director of the University of California Observatories, manages Lick Observatory, and with the California Institute of Technology, manages the W.M. Keck Observatory in Hawaii. So I hope to see you there. He served as director on the CARA board that oversees the W.M. Keck Observatory and has been director on the 30-meter Telescope International Observatory Board of Directors since 2005. And he's a time traveler. We're going to talk about that, right? You're a serious time traveler. How far back in time have you gone?
10 billion years.
10 billion years. Okay, so think about that. Andrei Linde here was born in Russia, as you will discover when he starts speaking to you with this beautiful accent that he's got. He gained his PhD from the Lebedev Physical, did I get that right?
Yes, kind of.
Kind of. Lebedev Physical Institute in Moscow in 1975.
He speaks Russian with a good American accent.
Я не знаю. Говори по-русски. And came to Stanford in 1990. During the 1970s, worked on models of the early universe, which contributed to Guth's proposal of inflation in 1980. Later suggested modifications to that theory to overcome some of its shortcomings. We'll talk about that. Creating what was called the new inflation, which he soon moved on from as well, and put forward a more general theory called chaotic inflation, which I thought made some reference to where I come in from in Washington, but it doesn't, just the chaos part. And he is a 2014 Kavli Prize winner in astrophysics. I should say, as I find my right page here, and point out very importantly that Michael here is sitting in for Jerry Nelson, who passed away in this last year, pioneering astronomer known for his innovative designs for advanced telescopes. And we're going to be talking about advanced telescopes. We're going to go from nanoscience to the brain to space. And I'm going to put this up, I think. There we go. Mirrors, telescopes, seeing as far away as we can. And this was Nelson's work, and you've been involved with this. What are we looking at?
Okay, so this picture is sort of the end of the story, at least up to now. I'm going to start with Galileo. So humans used to look at the sky. You can see about 3,000 stars from any place with your naked eye. And that was astronomy, and amazing things were done. People tracked seasons. They knew when to plant corn and things like that. But when Galileo first used that little tiny telescope, and it was only about that big, it had a 3-inch diameter lens, but most of that was masked out because it didn't work very well. He saw a bunch of things. He saw the phases of Venus. He realized that there were moons going around Jupiter. He, for the first time, looked at the Milky Way, this beautiful swath of stars that goes across the sky, and realized it was a swath of stars. Before that, people couldn't distinguish individual stars. So with that little tiny telescope, it completely revolutionized astronomy, and that's been the case pretty much ever since. So there are many, many smart theorists in astronomy. Andrei is one. I see Tom Abel, George Blumenthal is here. But it's a science, so the old Russian proverb, which is trust but verify. The verify part is what observational astronomers do. So starting with Galileo, people built larger and larger telescopes. And the advantage of that is with a larger either lens or mirror, you collect more light. You can see fainter things. You can look with magnification. And so telescopes got bigger and bigger. They made bigger and bigger lenses up into the late 1800s. The problem with a lens is the light has to go through it. So you can only support it from the perimeter. So as lenses started to get to be 36 inches and 46 inches in diameter, they were no longer able to support them from the perimeter. So people started to use mirrors. The advantage of a mirror is you can support it from the back because the light bounces off. So mirrors got bigger and bigger. And it turns out it's a property of glass that if you double the diameter of a mirror that's made of glass, polished on the surface, it has to get thicker by a factor of 4 every time you double the diameter. So biggest active, working, productive telescope that was built was the Palomar 200-inch. So it had a 5, we talk about the size of the telescope, it's the diameter of the primary mirror that collects the light. So the 200-inch or the 5-meter was completed in 1949. The mirror, the piece of glass that they polished, weighed 15 tons.
15 tons.
15 tons. So you can imagine that as you tilt the telescope around to look at different things in the sky, the gravity vector changes and deformations due to gravity could ruin the figure. So,
and you really don't want it to fall on you.
You don't want that, and you also, the Palomar mirror took 11 years for them to carefully polish the surface.
11 years.
11 years, because there's some amazing numbers here. You have to have on all scales, from very tiny scales to the full 5 meters, you have to have a surface that's precise to about 10 nanometers, 10 billionths of a meter, which is about 1/1000th the thickness of a human hair. So you spend 11 years doing that surface, you put it in the telescope. If you have any deformations that are bigger than that scale, 1/1000th of a human hair, you'll ruin the images. So building big telescopes is really hard. I think harder than most people realize. So in 1949, they finished that. The Russians, the Soviet Union actually, in the height of the Cold War, said, we're going to have a bigger telescope than they have. So they built a 6-meter diameter telescope, which sort of proved how hard it was to do this, because it made okay images looking straight up. But whenever they tilted it to look at a different part of the sky, the images went bad.
No, it's not only this. It's just when they transported it, some bolt fall on the mirror and they put a plaster in it.
Yeah, okay. So, I would claim that the best big productive telescope was completed in 1949, and the years went by. Up until then, people had built larger and larger telescopes. And every time somebody came in with a significantly larger telescope, all kinds of wonderful things were discovered. The expansion of the universe, the fact that the universe was made of many galaxies like our own, all of those advances in observational astronomy sort of came with each jump forward in telescope. But people were stuck. They really weren't sure how to make a primary mirror bigger than the Palomar 5 meter or 200 inch. So this is where Jerry Nelson enters the picture, and I have to say I'm tremendously honored to be here on Jerry's behalf. He's one of the nice things, I've been an academic all my life, well, ever since I became an academic. One of the nice things about that is I hang around with a lot of smart people, which is a real pleasure to interface with them. Jerry Nelson might be the smartest guy I ever knew. We worked together for 25 years. We were colleagues in Santa Cruz. So Jerry, who was a high-energy physicist, was pointed to this particular problem of how do we go beyond the 5-meter mirror size limit. And everybody else was thinking about how you make bigger boules of glass and how you polish them and how you support them up to 6 meters and then 7, then 8. Jerry said, oh, forget that. Jerry's approach to everything was if it wasn't excluded by the laws of physics, then it was possible. And all you had to do was be clever enough to figure out how to do that. So Jerry started to propose in the late 70s to, instead of building a mirror out of a single monolith of glass where you have these scaling problems, which have to do with the structure of glass, he said, let's build hexagons that fit closely together, and each one of those uses that scaling law in the other direction. So if they're only 2 meters, they don't have to be that fat. So the overall mirror can be much lighter. And people said, you're nuts. I mean, that's totally crazy, because even if you can make these segments, you have to somehow measure where one is with respect to the other to about 10 nanometers, to 1,000th of the thickness of a human hair. And at the time, those sorts of sensors simply didn't exist. Not in the lab. Forget doing it out in a telescope dome where the wind blows, the humidity changes, the temperature changes. So to Jerry, this was just a little challenge. Let's go figure out how to build.
Just a little challenge.
Yeah, let's go figure out how to build sensors that can measure the position of 2 big pieces of glass to 10 nanometers. They did that. They proved that they could do that. Once you know where the segments are with respect to one another, then you need to build actuators that can move them in tip and tilt and piston in the Z direction to that same precision of just a couple of nanometers. And that's what you have to do if you want to make what looks like a single surface out of segments.
Is that what we see here?
And that's what we're looking at here. So it's a little hard to know exactly what this is. We're looking down.
There's a person standing at the bottom of
yeah,
not.
Actually, it's all done with mirrors, it turns out. So we're looking down.
Is that you down there? Right?
Yeah, it is.
Is it?
Yeah.
Really?
Yeah.
Okay.
We're looking down at the primary mirror of one of the Keck telescopes. So Jerry, they designed and built the actuators, they designed and built the sensors, they built the system that took all those measurements and decided where to move the pistons. So that was 1979. A lot of people said, there's no way you can figure out the optimum position. Once you know everything, the optimum moves to the actuator. They built that control system. They built the segments. So this is a picture looking at the primary mirror of his prototype telescope, which was the Keck 1 with a diameter of 10 meters. So to test out all his theories, they built a very big telescope. So there are 36 segments there. Each of them is 1.8 meters in actually edge to edge, what the diameter means. And they all work together as a single, perfect 10-meter sphere. So everybody thought Jerry was nuts in 1979. They built the things. They demonstrated stuff up at LBL with some other colleagues, but Jerry was certainly the intellectual driver and the energy.
And how did he drive that? I mean, if everybody thought he was crazy.
Yeah, so that's a great question. So it takes a lot of things to accomplish something in the world, right? There are talented humans all over the place. So you have to be really smart. Jerry was that. You have to be very persistent with the problem. So when people say, that's never going to work, you're nuts, He had zero problem going to the lab and working with the folks, the engineers or the opticians or the Berkeley professors or the Stanford professors, wherever. Once he hit the edge of his knowledge on something like the elasticity of glass, he'd go find the expert and raise himself to that level.
And do it.
Just pure perseverance, and I think it requires a particular charisma. It's very useful to get people to come along.
Our next one, we have 5 meter, 10 meter, and 30 meter.
Yeah, so the little disc at the bottom, that's the 5 meter, 200-inch telescope at Hale. You can see the Keck 10 meter mirrors is much thinner. The surface density is much lower. It's a much lighter mirror, easier to build the telescope around and control. And one of the things that Jerry recognized way back in the late 70s when they did this is the segmented mirror design is intrinsically what engineers called scalable. You know, you build a 10-meter telescope with 36 segments. If you put another round of segments, then you have whatever you have, a 12-meter telescope. And you can do that pretty much forever, right? So it's a wonderful, scalable concept. Jerry's comment always was, it had legs.
Next.
So, well, just a second, go
Sorry.
back one more. So
Sorry.
what Jerry's been doing for what he did for the last decade of his life, and it's where we've interacted a lot, is once we built the 10-meter telescopes, we proved they work. We did all kinds of science. It was wonderful to be at the University of California at Caltech, the two owners. We said, what's the next step? We were actually asked by someone, what's the next step? What could you do if you had $1 billion for the next generation giant telescope? And we picked 30 meters for lots of reasons, but the basic reason is with a 30-meter telescope, we believe we can look all the way through space-time to the beginning of the universe.
Okay, so this is where the time travel
This is
thing
the time
comes in.
travel.
This gets a little weird, but amazing. Say that again.
Yeah, so
You can look all the way through the universe to the beginning of time.
if we look at the sun, turns out it takes light 8 minutes to get from the sun. So we see a picture of the sun as it was 8 minutes ago, which is pretty much just what it looks like now. If you look at the nearest stars to the sun, they're, 4, 10 light years away. So the light has been traveling. We take a picture of that star, we see it as it appeared 4 years ago or 10 years ago. If you look across our galaxy, it's about 50,000 light years in radius. So at the outskirts of the galaxy, we see what things look like 50,000 years ago. So in that sense, telescopes really are time travel machines because we can really look at what things looked like 50,000 years ago. When I was a grad student, we could look back about 2, 3, 4 billion years with the telescopes of the time. That was before the Kecks, that was before the Hubble Space Telescope. And so that's kind of the universe we knew, within 4 billion light years and back to 4 billion light years from the present. So when we said, what's the right size next telescope to build, one of our primary science drivers was we wanted to be able to see the universe is 13 billion years old. We wanted to see things that were 13 billion light years away. So we could watch, as it happened, it really is a picture of the universe 13 billion years ago. We could watch the formation of the first stars and galaxies and whatever unusual objects ended the cosmic dark ages. So that was one of the scientific drivers to pick 30 meters, is to look all the way through space-time.
How do you process that you're seeing that and experiencing that?
Well, it's what astronomers have been doing for a long time.
I know,
It's been
but
20, 30 years now. We've really started to push back to distant enough objects that we really are seeing the universe at an earlier phase. Well, I saw Garth Illingworth in the room, one of the astronomers who's pushed this as far as you can go with Hubble Space Telescope and Keck.
And in seeing back that far and out that distant, the ultimate question that we would ask is, what will we find, and will we find life?
Oh, well, those are two different questions.
Sure.
I bet if we discover evidence for life, it's not going to be in things that are 13 billion years in the past. That's probably something that's going to happen very close to the Earth. Yeah,
I want to
let's
show you
see.
this one, and then we'll
Yeah, okay.
on to
Yeah,
so this is fascinating in several things. Tell us what we're seeing.
Yeah, so these pictures just sort of demonstrate some of the science case that we've put together. as we're trying to get the 30-meter telescope funded and built. You always start with science drivers and use that to define what facility.
Start with that in the upper right-hand corner, because
Yeah,
that looks like something out of...
Okay, the upper right-hand corner is what some people think telescopes should do. Those are two Keck telescopes on the left, and on the right is the Subaru 8-meter telescope. And you can't quite see, but off to the left of the leftmost Keck is the 8-meter Gemini telescope, and they all have laser beams firing out of the domes, pointing toward the center of our galaxy, where there's a supermassive black hole. So if we really had a long time, we could talk about why these telescopes are shooting laser beams
Well,
out.
could you give us a hint?
I'm going to give you the 1-minute version of that. As you build a larger primary mirror, in theory, you can image things more sharply. It's linear. If you build a mirror that's 2 meters in diameter instead of 1, you can image twice as sharply in the sky. So all these years we've been building bigger telescopes, we caught more photons, and you'd say we should have been seeing sharper and sharper visions of the universe. But it turns out, because we're at the bottom of the atmosphere, it's like we're looking through a Coke bottle. And light is blurred to the equivalent diffraction limit, we call it, sharpness limit, of a 6-inch telescope. So when we built 12-inch telescopes, we got more light, but we didn't get a sharper image. So that all changed about 15 years ago, and Jerry Nelson was also one of the pioneers in this, when astronomers figured out how to measure how turbulence affects light coming down to the ground and send that signal to a deformable mirror and correct to the diffraction limit of the primary mirror. So we can take all the blurring of the atmosphere out. So all of a sudden now, if you have a 10-meter telescope, you can image 5 times more sharply than the Hubble Space Telescope can, because it only has a 2.4-meter mirror. And with a 30-meter telescope, we can image 12 times sharper than the Hubble Space Telescope. Okay, so those are what those laser beams are for. They help with the adaptive optics. The lower corner is what you just referred to. I think the
Lower right or lower left?
Lower right.
Lower right.
Thank you. The 30-meter telescope will make all astronomy easier. But I think the two marquee cases, we talked about one, will look all the way through space-time and image the universe at its very earliest times. But the other thing we can do when we have these very sharp images is we can isolate stars from the planets that are orbiting those stars. And with a 30-meter telescope, we can take spectra of individual planets orbiting other stars, and we can look for signs of life. And I think that's going to be enormously exciting.
Andrei, you told me when we spoke for the first time, and this is, one night you woke up, your wife, is she here with you?
Yeah, she's here.
She'll tell us if this is true or not. And she said, and I'm quoting Andrei here now, "I think I know how the universe was born." Now that would be, I think, a rude awakening or an amazing awakening, but that's just an amazing thing for you to say. But what I'm really interested in is, what did she say to you?
Well, she is a professor of physics here, so
Oh,
if
wow,
I
okay.
will cite exactly what she said, this will not be for a easy discussion, because it's like de Sitter space, exponentially expanding universe, Hubble constant, and all of this, and the bubbles are forming, and then the bubble which is forming, it must form softly enough so that the universe appears gradually. Lots of technicalities. But the main idea is like we're trying to reverse engineering how the universe was born. If we think, well, just imagine that you are God, you want to create a universe. Okay, just imagine. Okay, so now look at this big telescope, at any of them, you see huge amount of matter. Now think about all of this matter. In the beginning, it was in one place where it was exploded. One place maybe, or maybe it was a huge place. How much matter do we need to create whatever we see right now? In accordance with the Big Bang theory, which was popular at that time, you need approximately 10 to the degree 85 grams of matter. And all of these should be like compressed into a small tennis ball and then exploded with accuracy like 1 millionth. at the same time everywhere, and then, oh my God. So who gave you this 10 to the 85 grams of matter? So if you reverse engineering the creation of the universe, try to think how you would do it. You try to think it differently, and Alan Guth here at Stanford suggested here some interesting idea how you can create the universe. And then in the end of his paper, have written that unfortunately it does not work for this and that reason, but this is the reason for us to think about it, okay? And then the mail from US to Russia was traveling long time. I knew that it is possible to do maybe something related to that, but there was a trouble how to do it. And then a year later, Alan Guth with his collaborator have written a 100 pages paper proving that it's impossible to improve what he did. And fortunately, because the mail was so long, I received this preprint saying that it's impossible to improve after I already improved it. So that was exactly what I was talking to well, my wife about this night. Okay, and yeah, it was interesting awakening. Anyway, so then we worked more about this. The whole thing is like science fiction, because normal story is that you have this matter and then it expands, and what you have, what you started with, you got, okay? So you cannot get matter from nothing, because you have energy conservation, matter conservation. Everyone in school teach you that, okay? And then now we know how to make the whole universe from less than 1 milligram of matter.
From, wait, from less than 1 milligram?
From less than 1 milligram of matter.
Should I put your slide up?
And what?
Should I put the slide up?
Oh, okay.
Okay, there we go.
Oh, yeah, okay. So this thing in the, oh, yeah, my God, Russian cannot come without laser weapon. So this is, this is a Big Bang, okay? And here is inflation. And previously we thought this is a Big Bang, that's the whole story. And what we found that maybe inflation is the way how Big Bang works. So you may start with some heavy energetic nothing, like vacuum, okay? Nothing, we have lots of it. Now, heavy energetic, this was some interesting idea. And then imagine that nothing grows, and it costs you nothing, because whatever, okay? And then it grows, and then it decays. But it costs you no energy for nothing to expand, right? So no non-conservation of energy. Oh, I am cheating here a little, but it's okay. Well, and after that, when it expanded, it produced all matter. Okay? So the thing was how to make it expand fast enough so that the universe will grow big enough, and how that after this Big Bang, after the inflation is over and this vacuum decayed, how to produce matter. So that was, well, set of tricks which we did on the way, and it also looked impossible because it looked like it expands faster than speed of light, which is forbidden by Einstein theory. So many things which were forbidden, and we learned how to do it, okay? So that is, well, reverse engineering, and if you show the next slide, this is like an evidence of what we, at that time worked about. It looks really weird. What is so great, this Planck satellite, it's $1 billion, okay? To test this crazy stuff about this, well, looking like a cheating thing. And these people from Planck, when they obtained this image, they were asking me, what is going on? We were traveling along the United States, and we are showing them this image, and nobody is excited. Because they say, well, we go to Home Depot and we buy spray, and they spray it for much cheaper, okay? So what these things are is during this tremendously fast expansion, quantum fluctuations, and this happened at approximately 10 to the degree minus 35 seconds after the Big Bang. So this is the Big Bang, inflation starts, bach, everything is over. During this time, quantum fluctuations are produced, and they're stretched on the size larger than everything that we can see at the moment. And this is the photograph of these quantum fluctuations produced at this moment. And our universe allows us, using these telescopes, now we're using telescopes like huge microscopes, looking back in time to the moment 10 to the minus 35 seconds, and we see these quantum fluctuations produced. And according to the theory, the quantum fluctuations of temperature, they are simultaneously responsible for galaxy formations. And then we say galaxies are children of quantum fluctuations produced at this moment. And we are children of galaxies, so we are grandchildren of these quantum fluctuations. And of course, it sounds like nonsense. So the first thing which after finding the way how to do it, I said the people who invented the theory of these quantum fluctuations, one of them, Mukhanov, was working with me at the same Lebedev Institute. I told him, this is nonsense because you cannot produce anything classical from something quantum. And then gradually learned that that's what we are doing. That is what inflation is doing. That's what we see right now. And if you show the next one. Oh, yeah, I'm sorry. Taking comment line. Okay, sorry.
That's all right. This will be quick because I want to get to the next slide, the multiverse. That's when it really gets interesting.
Yeah. So these are results of this experiment, Planck experiment, translated into something. We study distribution of different spots at different frequencies, different size, and there's a called spectrum. And the spectrum is shown how they are distributed with respect to some angle. And what we see, this green line, these are predictions of inflation. Red spots, the experimental data. Here, the theoretical predictions are a little bit uncertain, and experimental data are a little bit uncertain as well. But here, everything precise. Each spot can be considered as a separate experiment. And everything so far just looks spectacular. And maybe we can do even better than that. Like here right now at Stanford, we have this, bicep experiment and CAC experiment together. People are sitting, and the North Pole, Xiaolin Ku is, here he is working on that. Maybe they will be able to find some additional quantum fluctuations which are also predicted by inflation. They are weaker, but if they are found, that is just really science fiction, because they are finding gravitational waves. So one of the most spectacular things happening, which happened it was this year, right? The people who found, not this year, but the Kavli Prize, the previous year, when they found gravitational waves propagating through the universe. So they are classical gravitational waves. They are produced by normal bodies not far away, relatively a few billion light years, 1 billion light year. But this story, what we are trying to study right now, gravitational waves, quantum produced, if they are found, it will be a confirmation, not classical general relativity, but quantum general relativity. This is just a dream.
Andrei, let me move to the multiverse here instead of the universe.
Oh, yeah.
And if you want to sit down here, I want to have you back on them. And then we're going to do very quickly to some questions, and then we need to move everybody on. But it's the inflationary multiverse, and that's old Albert Einstein hanging around there.
Yeah, and if you look at the bubble down, this is how we thought the universe was born. This is something produced this big bubble, and this big bubble is the universe. Instead, you do it once, and if you are successful to do it once, you can also do it twice, you can do it 3 times, more times, and each time when you are doing quantum mechanically, it's possible, then you produce different parts of the universe with different properties. You produce red universes, you produce blue universes, and each of them is much greater than what we can see now in the best telescope, And then we ask a question, so why do we live in a yellow universe, for example? Oh, well, maybe we cannot live in the red one because life of our type is impossible there. So that's why all Einsteins here, they live in yellow universes, and maybe there are many different types of Einsteins, and there are many different, Kavli prizes and committees, and Stanford University is there. So our universe is a multiverse with different properties at different times. That's the universe which becomes immortal.
Can you see a multiverse?
We haven't figured out how to do that yet, but we are not going to rule it out since it's Andrei's theory.
And what does this mean for us?
Well, let's say this. there is a moment when we maybe thinking about science in general slightly different than what we were thinking before. Because one of the dreams of Einstein, which is not occasionally here in the picture, one of the dreams of Einstein is to find a theory which uniquely prescribes these are the only possible coupling constant and masses and everything which are logically possible. Only one theory which is possible and everything else is not the case. So he had the dreams of final theory. He tries to understand, why our universe is so uniform. And he invented something which is called cosmological principle. And I did not know that he invented it, so I used to make a joke that some people who do not have good ideas, they have invented principles because there was no clarity why this principle worked. So now inflation allows to understand why he was right that our universe is everywhere the same in the yellow part of it. But if we consider the whole universe, then the whole idea that you have one law of physics for everyone becomes unnecessary. It is what we see right now, that the mass of the electron is everywhere the same, to the right planet, to the left planet, to the right galaxy, to the left galaxy. No idea whether electron even exists in yellow and in green and blue universes. And according to string theory, which was also developed here in a substantial way at Stanford, there are maybe 10 to the degree 1,000 different colors for the universe. So our understanding of the universe have changed dramatically during the last years. And maybe some of these we will be needed to take back because we're trying something which nobody have done before. Some of it must be wrong in many aspects, but some of them may be right.
Let me take our conversation and both turn it and conclude it with a question from the floor, which really is all about this theme of the future and what we're here for. What are the next big questions, this question asks, what are the next big questions that you expect can be answered from astrophysics within our lifetimes? Now, within our lifetimes depends on who's asking the question, but I take the point. So shall we say 50 years? That's optimistic for me, but I'll go there. What do you think?
Well, I mentioned two already. One is first light, post-inflation, post the hot Big Bang. The universe was expanding, but too hot for things to form into galaxies and stars. At some point, those are the cosmic dark ages after that. At some point, things start to do that. And I think understanding the first birth of stars and galaxies and their evolution up until this time is going to be a major part of astronomy research for the next 50 years. And I think that's easily within reach, so it's not so interesting in some ways. The other thing is, 15 years ago, the only planets we knew about were the ones in our solar system, plus Pluto. We now know that the galaxy is absolutely chock full of planets. And so I think this whole question that, people didn't even take that seriously about looking for life in the universe, intelligent life is yet another step. All of a sudden, that seems like a very serious part of astronomy research, and I think that
looking for life.
Looking for life. I think it's one of the most exciting futures of the next 50 years.
That is amazing. Andrei, next big question.
Well, I don't think that we know what will be considered next big question in the next 50 years, and probably not everything, not anything that we are speculating about right now. What I can say that for me, for theoretical cosmology in general, one of the issues is that we need to merge somehow to learn how to live with quantum mechanics applied to our universe as a whole. So whatever I have shown you, this Einstein, etc., this is like cartoonish picture of the multiverse. But we understand that we need to study this quantum mechanically. We need to apply different rules. And in quantum mechanics, there are questions formulated in crazy way, like what is reality in general? And what is the role of observer in quantum mechanics? And then when I study the universe, I know that I cannot convincingly answer many of these questions before I understand what consciousness is. is. And therefore, and I'm taking it very, very seriously, I expect that the real progress may be achieved in the areas which either join us to other people who study consciousness, or will be somewhere at the boundary between these, something which is philosophically very, very challenging. So it is not only astrophysics and cosmology. I am interested in the universe, because for me it is poor man model of life of a person.
Poor man's model of life. Well, we have had an unbelievable journey here this afternoon, from nanotechnology and nanoscience to neuroscience to this astrophysics, where we contemplate our universe and life and how it all began and whether there's life out there, never mind whether it's intelligent life, accompanying on this journey. I think that this is validation of what Stanford does and stands for, and what Kavli does and stands for and supports. The search for knowledge for itself, discovery, curiosity-based or otherwise, is vital. We need to tell that story better, both within science and without, and through media and through our schools. And I think this is a great way to celebrate unbelievable success and remarkable people. So please join me in thanking all of our panelists here this evening. Thank you. And I am now, thank you so much. Andrei, that was great. Thank you so much. Thank you so much. And thank you for bearing with and making use of Pigeonhole. Those were great questions. It's now my pleasure to turn the program back over for recognition of our laureates to President of the Norwegian Academy of Science and Letters, Dr. Ole Sejersted, for the recognition ceremony. Sir, it's over to you. Thank you so much.
Thank you very much. That was a fabulous session. We are a bit over time, but we have reached the most important part of this meeting, the recognition ceremony. So let me start by thanking the laureates for the insights into their own extraordinary scientific achievements, as well as the challenges that lie ahead for the world's young scientists. And thank you to Frank for leading such a wonderful discussion. We now want to formally acknowledge the Kavli Prize laureates that are with us today. We would also like to recognize the institutions where the prize-winning research was conducted. And these institutions were vital to the discoveries recognized by the Kavli Prize. And they continue as powerful engines of science that benefits all humanity. So let us first start with recognizing Donald Eigler, former IBM Fellow and 2010 Kavli Prize laureate in Nanoscience, for his development of unprecedented methods to control matter on the nanoscale. And representing IBM Almaden Research Center is Director of Science and Technology, Spike Narayan. Dr. Narayan will give a few remarks on behalf of IBM and Dr. Eigler. Please.
Thank you, and thank you for the invitation to join the festivities today. It is indeed my privilege and pleasure to say a few words on this great occasion. As the Director for Science and Technology at IBM Research Almaden, which is just 25 miles south of here, it's one of the remaining corporate labs that still support fundamental science in a very big way at many different levels. Dr. Don Eigler, the 2010 Kavli Laureate for Nanoscience, spent 25 years in our lab and did his exciting and now truly legendary work on probing at the nanoscale. He used the scanning tunneling microscope tip to manipulate materials at the atomic scale and measure properties exactly at that scale as well. Truly remarkable. This opened up a whole new field of probing at the nanoscale, which continues to be a vibrant area of research today. Along the way, of course, he took the famous picture that he talked about during the panel session, the IBM spelt with xenon atoms. The STM lab continues to do groundbreaking work today, and that was a tone that was set by Don Eigler way back about 15 to 20 years ago. His lab continues to push the boundaries of science by exploring phenomena at the atomic scale. To name a few things, the team actually measured the force to move a single atom. It also figured out the number of iron atoms it will take to store 1 bit of information reliably. That happens to be 12, interestingly enough. And more recently, they actually demonstrated that you could store one bit of data on a single holmium atom. For those of you who haven't heard about holmium, it's a rare earth metal with atomic number 67. So this team of incredibly bright individuals that did a lot of this work, many of them are actually in the room today, and you'll get a chance to see and talk to them today. Wonderful team that Don assembled over the years and continues to influence the work that's being done in the lab. Now, Don's fascination with rare or noble gases was not limited to xenon. And as you heard during the panel discussion, he even had dogs named after rare gases. The 2 dogs that I know is neon and argon that spent many, many years in the lab and were a fixture in our organization. I do not know if krypton or radon is in his life. Maybe you can enlighten us about that. I did not mention helium because I think he was married to liquid helium for 25 years that he was in the lab. It is something that he could not do without. On a more serious note, though, you have great scientists, and you have great scientists who are also leaders. And Don is actually the latter. The reason why I say that is to be called a leader is not about how he or she leads, but it's about how they create leaders. And Don falls into this category of creating leaders because the STM lab certainly over the years created a steady stream of leaders in that field. All you have to do is look around and see where all his postdocs are today. And a huge number of them are there in this room today, I'm proud to say. Wonderful set of postdocs that have gone on to do great things in different institutions around the world. And all this was possible because Don, who never for once worried about giving credit to junior scientists. And this is a sign of a true leader and a precious quality to possess. And Don had that quality of creating leaders and pushing them forward into the world stage. So let me take this opportunity to thank Don again for your great work at IBM. And I'm also so glad that the Kavli Foundation recognized this amazing body of work in a timely fashion. Let me also extend my hearty congratulations to all the other Kavli laureates in the room today. Congratulations. And finally, I would like to thank the Foundation for continuing to recognize and reward breakthrough science across the globe. Truly a remarkable organization. Thank you again.
Ask Dr. Eigler to come up. Then we move to the 5 Kavli Prize laureates who are currently or formerly affiliated with Stanford University. They are Andrei Linde, 2014 Kavli Prize laureate in astrophysics for pioneering the theory of cosmic inflation. It is Carla Shatz, 2016 Kavli Prize laureate in neuroscience for the discovery of the mechanisms that allow experience and neural activity to remodel brain functions. It is Richard Scheller and Thomas Sudhoff, 2010 Kavli Prize laureates in neuroscience for discovering the molecular basis of neurotransmitter release. Unfortunately, Professor Sudhoff could not join us today. It is Calvin Quate, 2016 Kavli Prize Laureate in Nanoscience for the invention and realization of atomic force microscopy, a breakthrough in measuring technology and nanosculpting that continues to have a transformative impact on nanoscience and technology. And then I will ask the Provost, Vice Provost and Dean of Research, and Arvin, to give a few remarks on behalf of Stanford University and the 5 Kavli Prize laureates. Please.
Thank you very much for this opportunity to share a few more words about our wonderful Stanford Kavli laureates. The science that they've done and for which they've been recognized has been presented, as you've heard and enjoyed over the afternoon. So I was asked by the Kavli Foundation to say a few words about their service and their role in contributing well beyond their science to our institution. So I'll begin with Andrei Linde, and in his case, it's easy. He is noted for his dedication to undergraduate teaching. At Stanford, he teaches Physics 23, which is taken by biology and non-physics majors. He's also been lecturing in a freshman course that looks at cosmology from the perspectives of both physics and philosophy. I think we'd all love to take that course. He has a reputation that his session on inflationary cosmology is by far the high point for the students in this course, and I think we can absolutely all see why that would be the case. In both courses, his students really comment and appreciate on his enthusiasm for science, which is infectious, and that commitment to undergraduate teaching is certainly exemplary service. Calvin Quate has been a leader in many, many ways at Stanford. He was the co-founder of our applied physics department, and during his long career, he dedicated himself to a number of leadership roles, including chair of applied physics, chair of electrical engineering, associate dean for natural sciences, and in the words of one of his colleagues, Cal is the prototype inventor physicist the department has tried to emulate for so many years. He is an inspiration to everyone he interacts with, certainly a remarkable service over many decades. Carla, as you heard, Carla Shatz was the first woman chair of a department of neurobiology at Harvard, among very many firsts, and representing service not just at Stanford, but at Berkeley and Harvard. In 2007, we were very fortunate to recruit Carla back to Stanford as director of BioX, which is our premier interdisciplinary biosciences institute. As she said, she and I were actually assistant professors hired the same year, took a big risk here at Stanford that year, and we joked that with her recruitment back here, our, let's say, older girls network finally paid off. As BioX director, Carla works tirelessly every day to help our faculty and students achieve their research and education goals. Tremendous service on her part. Richard Scheller, although he left Stanford, he was here for 19 years as a dedicated researcher and teacher. Subsequently, he has continued to serve as a very valued advisor who gives us input about our biomedical sciences programs at Stanford. He's also a campus resident where he, along with his fellow neuroscientists and his wife, Susan McConnell, who's a professor and HHMI investigator at Stanford. And just a family note, Sue was Carla's postdoc at Stanford. Finally, we mentioned Dr. Sudhoff, who was not able to be here today, but is certainly renowned for his efforts on behalf of all of us here at Stanford. So thank you to all of our laureates.
So may I ask the laureates to come up and line up next to Anne there? So if I can go Anne, if you go on the other side of Anne.
Okay, he wants us to take our badges off. Where are you going? No name tags. No name tags. Okay. So this is for me to try to hold up. There we are. All right, everyone.
Then we have come to Mike Merzenich, 2016 Kavli Prize laureate in Neuroscience, who along with Professor Shatz won the Kavli Prize for the discovery of mechanisms that allow experience and neural activity to remodel brain functions. His affiliation with the University of California, San Francisco, and Executive Vice Chancellor, Provost, and Professor Daniel Loewenstein will give a few remarks on behalf of the University of California, San Francisco, and Professor Merzenich.
Thank you so much. I'm just thrilled to introduce my colleague, Mike Merzenich, who's the co-recipient of the 2016 Kavli Prize in Neuroscience, and he's in very good company with Carla and with Eve Martyr. Mike is the Francis Sui Professor at UCSF, and he's been honored with this prize because of his work on plasticity. So I'm going to actually dispense with all the rest of my notes because you got such a good feel for the kind of work that Mike has devoted his entire career to, brain plasticity, and instead, very briefly, tell you two personal vignettes in the way Mike has intersected with the UCSF community in a slightly different way. You wouldn't expect this. First, in 2009, the Iraq Action Group at UCSF developed relationships with the healthcare professionals in Iraq to try to provide some help in such a disastrous situation. And we learned about a young boy, his name is Mustafa Ghazwan, who was 3 years old and completely lost his hearing because of a bomb blast that took place in his backyard. He lost a number of his extended family, but his parents reached out to the health professionals there to see if there was any help they could get. We heard about him at UCSF, and we were successful in bringing Ghazwan and his family, Mustafa and his family, over to our hospital. And because of Mike Merzenich's discovery of the cochlear implant, Mustafa is a healthy 10-year-old, 12-year-old now, living in the Bay Area with his family with full hearing. The second vignette is as a neurologist and a neuroscientist, I get the chance to be the course director for the neuroscience course that all of our UCSF medical students are required to take every year. And we teach them about the normal function of the human nervous system and the diseases that can affect it, from Alzheimer's to autism and so forth. But it struck me about 10 years ago that we don't spend any time with our students trying to show them that there are ways to improve the performance of a well-functioning human brain. So as part of this, we created a course called Training the Mind. That is an elective course that a number of our students take, and one of the key faculty in that course has been Mike Merzenich. So I'll conclude by saying that the paths of inquiry that Mike has opened up in the areas of neuroscience and neurology have improved truly countless lives. And I want to thank the Kavli Foundation for honoring Mike and the other laureates in this very meaningful way. Congratulations, Mike. Okay,
So, yeah. So lastly, we want to honor Jerry Nelson, 2010 Kavli Prize Laureate in Astrophysics, for his contribution to development of giant telescopes. Professor Nelson passed away in 2017, and we all felt the loss of this pioneering astronomer. He was affiliated with the University of California, Santa Cruz, and Chancellor George Blumenthal will give remarks on behalf of University of California, Santa Cruz, and Professor Nelson. So please.
Thank you and good afternoon. I'm truly honored to be asked to speak today about Jerry Nelson, who I had the great fortune to know in many capacities. Jerry was a longtime UC Santa Cruz professor. And as the UC Santa Cruz chancellor, I couldn't be more proud of the plaudits that have been bestowed upon Jerry, which frankly, they're all so richly deserved. The Kavli Prize itself also brought great recognition to our campus. As you know, Jerry's work on the design of telescopes was truly revolutionary. He was the first to propose the segmented mirror design of the Keck Observatory twin 10-meter telescopes, as you heard a few minutes ago from Mike Bolte. You know, his concept, I have to remind people, was not fully embraced when he first proposed it. In fact, wacky is a word I heard thrown around more than once. Well, Jerry's design proved to be genius, and his work empowered astronomers throughout the UC system and beyond. And I truly believe that Jerry owns a piece of all of the discoveries that have been made in the last 20+ years of the Keck Observatory. I think it's a wonderful legacy that will live on in the 30-meter telescope that is now being built. And I'd like to remind people that Jerry's brilliance extended beyond just this innovative design. Jerry also developed new techniques to fabricate and control mirror segments. And as the founding director of our Center for Adaptive Optics, he helped pioneer the general use of adaptive optics in astronomy. Remember, as you heard from Mike Bolte, that adaptive optics is how you take the twinkle, twinkle out of the little star. His work in total brought a great recognition to our university and had a profound impact on all of astronomy in the 20th century. As a colleague in the Astronomy and Astrophysics department, I admired how Jerry could systematically and logically address a problem. And he was not only smart and tremendously skilled, he was a wonderful teacher, patient, and he never dismissed those who knew less than he did. That all made an incredible package. And finally, Jerry was also a good friend, generous, personable, collegial, and remarkably unpretentious for someone of such renown. I miss our conversations, his easygoing smile, and those horribly loud Hawaiian shirts he wore every day. I have great memories of the times I've spent with Jerry, and chief among them is the wonderful visit we made to Norway together with our wives when he was awarded the Kavli Prize. I never imagined I'd see Jerry in a tux, but for the record, he looked great. In closing, I'd like to thank the people behind this honor for Jerry, the Kavli Foundation. It was a very thoughtful gesture, appreciated not only by my university, but by Jerry's family as well. In today's world, where the value of science and scholarship are too frequently called into question, the work this foundation does, promoting public understanding of scientific research and supporting scientists in their work, has never been more important. So thank you for the work that you do, and thank you for paying tribute to a very deserving friend and colleague. His legacy lives on through the incredible work of many of those in the room today. Thank you very much.
Yes. And then I'll ask Jerry Nelson's daughter, Alexandra, to come to the podium. his wife. I didn't know that. Sorry about that. So, no, that's Jerry Nelson's wife. Thank you very much. Thank you.
Thank you so much.
Okay. Thank you all for attending today's Kavli Prize event, honoring the Kavli Prize laureates in the Bay Area. And we now invite you to attend the reception, which is being held directly outside of the McCaw Hall in the foyer of the Alumni Center. So thank you for being here.